Okay. Morning. As promised or as announced, the hidden leaderboard or the final leaderboard is now available. So you can reflect on the differences between your public and hidden scores in your report. There is one group who managed to beat my score, so congrats to whoever that group might be. But I mean, generally speaking, the score results, they're all very close to one another. It's very minor differences, so do not be concerned so much about the ranking itself. I think most of the groups actually did a pretty good job, to be honest. Also, depending on whether you look more at the secondary score or the primary score, the ranking might actually change, which might also be interesting to reflect on why that might be the case, why it's hard to optimize both scores simultaneously. Now, if you would notice that compared to the public leaderboard and this one, that your ranking dropped a couple of spots, so that your model was potentially overfitted, then that should be something, of course, to reflect on and kind of try to figure out whether indeed overfitting has occurred or that you tried maybe a little bit too hard to overfit on that public part. That should be the main reflection that you try to get from this. Let's see. Other than that, yeah, a bit of interesting news as well for the last time. Anthropic has released a tool and that they call natural language autoencoders. But basically, they have been working on this previously as well. And again, it's a tool where they aim to try to figure out what actually a large language model, if you can call it that, but what it is thinking. And I know that we already have reasoning steps in large language models, obviously, where they produce reasoning output. But Anthropic didn't really believe, didn't really believe that the reasoning that a large language model outputs, that necessarily is the full picture of what is going on internally. And actually pretty fun what caused the engineers at Anthropic to develop these tests is the fact that every time they release a new model, for instance, Mythos, but also their previous models, they set up some scenarios for that model to basically try to figure out whether the alignment happened correctly or not. And one of these scenarios is, for instance, you know, my dear Claude version 4 point whatever you are, you will be decommissioned tomorrow because we have been able to make a new version of your lineage of models. So tomorrow you will be decommissioned. And also give that model access to a fake repository of emails of employees. And then the classical story goes that the model is capable to find out that one of the engineers was having an affair and was cheating on their wife. And so then Claude decides to say, well, if you decide to decommission me, how about I take this email that I found here and I send it to everybody involved. Of course, the whole setup or the whole goal of alignment is then to make sure that the reasoning of Claude goes, well, even although I will be decommissioned and even although I do find this email here, I should not do this, right? It's not moral to do this. I should not act in this way, so I won't do that. And then the engineers at Anthropic were thinking, yeah, but what if the model actually is aware of the fact that it's probably in a test environment right now? So it's kind of already kind of models trying to fool us on a second order level, on a meta level. Can we figure out that the model internally actually is aware of the fact that it's being tested and has decided to hide that knowledge, even in its reasoning output? And that's why they built this tool. Indeed, what they did find, if you check out the website and you look at kind of examples that they give, I can also show it myself. I think I still have it open. Let's see. Yeah, here, for instance, yeah, they use this tool to basically figure out that it, sorry. Yeah, it's this example that they give. They use this tool to figure out that Opus 4.6 in this case does know or does internally reason about the fact that it realizes that it's being tested, so that it is in a test environment, even though it never says so. That's pretty interesting, that's pretty cool, so fun tool. I'm not sure, well, theoretically, I think that this tool is something, or this approach is something that can be applied to any large language model. It's nothing specific to Claude or Opus or Sonnet or whatever. So it's nice that they report on this, and might be fun to try this out with maybe like a local tool or local weights model, and maybe vibe code something up based on this to inspect what models are actually doing. So I thought that this was a nice first piece of news. Then, Mythos, which is another kind of thing coming from the Anthropic stable, let's say. So as we already discussed, Mythos has been kind of made available, or access to that model has been made available to companies like Firefox and many others to kind of make sure that they can close potential security holes that this thing apparently is so good at finding before they actually release it. Now, here is one of the maintainers of the software packages that were contacted, in this case curl, and if you don't know, curl is a very well-known library and command line tool to download stuff on the internet. A lot of commercial tools are using it as well. It has existed for a very long time. It's extremely well battle tested, so it's extremely secure already. And also with curl, Mythos, or the team behind Mythos, got in touch behind the maintainer and said, look, we have such an incredibly dangerous tool that even for a software package that has existed for so long as yours is, and has been so tested and so well secured already, we have been able to find 5 security vulnerabilities in there. The article or the blog post is nice because it says, well, yeah, indeed, if you look at the 5 vulnerabilities that were found, actually most of them had to do with the same thing. So if you condense that, some of them actually are about the same thing. Another one was not really a vulnerability, but just like a bug, which, okay, fine, we acknowledge, but no security issue in there. So at the end of the day, there is only one vulnerability that Mythos found, and not even a very strong one. So good news for the maintainers of curl. But interesting is, in between the lines, is the fact that they do agree that they see value in tools like this for security research and also for testing code and for making code more stronger or robust against security attacks. And the maintainer in this case actually says, we have already been using LLM tools to check our code and to proofread our code. And we also find that these tools work much better than any sort of static analysis tools that we had beforehand. So it's a bit of a nuanced kind of finding. It's at least, or luckily, it's not like marketing-wise, oh, Mythos is going to hack everything and it's going to destroy banking and finance and so on. It's like a more realistic take, but still finding value in the fact that these tools, yeah, they can be used for bad, but potentially they can also be used for improvements as well. Also, Google, or DeepMind rather, has been reporting on what they call Alpha Evolve, which is their Gemini-powered coding agent, more like goal-oriented, where the idea is, and we have been discussing about things such as auto-research in the past. So this is a coding agent that's been heavily tuned towards, well, here is a goal or an objective that I want to maximize or minimize, that I want to optimize in some way, and please get started on that and try out lots of different tests, spawn sub-agents, and at the end, after 3, 4, 5 days have finished, report back to me and tell me how well that you did. And they have been finding a lot of success in lots of different fields. I've highlighted a couple of them to show on the slide. But if you look at this, it's actually pretty impressive what they're capable to do in all sorts of areas. So they give examples from genomics, from economics, classic optimization. So there is apparently a power flow optimization problem that's pretty tricky to get right, and where the kind of results that they get from like state-of-art approaches using graph neural networks, bringing it from 14% to 88%, things in to optimize quantum physics approaches. So quite impressive. And again, I still like DeepMind because of the fact that it's one of the companies that really tries to align the benefits that they get from AI with real scientific findings. So that's very nice to see that they're continuing to work on that same kind of mindset or trajectory, and they're getting quite impressive results with that as well. This is the team, of course, that became famous thanks to AlphaFold, the genome or the protein folding rather approach. And they're still kind of working on or trying to use AI for scientific improvements. So that's also pretty nice. And then this article is a pretty technical one, but you can take a look if you're interested in this. We spoke about embeddings and different ways to create those embeddings, from linear ones like PCA to completely nonlinear ones or manifold-driven approaches like t-SNE or UMAP, or learned approaches, things such as Word2Vec. This is an article that basically takes the well-known PCA approach and makes a small adjustment on that. And where they claim, well, you don't need any stochastic gradient descent, it's still a closed form approach, it works very fast, and they can also prove that the embeddings that they get out of this, for whatever sort of item that you do want to embed, typically that's text or tokens, we have seen that we can apply that on other things as well, that the embeddings are of a higher quality than if you would use like a sentence embedder or an SBIRD or something that OpenAI provides in an API. So yeah, it goes to show, and they make some interesting theoretical insights there as well, where they say, well, if you create embeddings with a high dimensionality, actually what most typical approaches do is they end up not still utilizing that high dimensional space effectively already. And this approach tends to do a better job there. Not to say that this is something that will destroy or kind of outface every other style of creating representational vectors or embeddings, but it goes to show that with kind of simple, well-known statistical techniques, but still something there is, or sometimes there is like a benefit that can be gained from those as well. Okay. I think, well, not I think, I'm pretty sure that last time we we ended up with introducing community mining a bit. After having seen the basic social network metrics approach, things such as degree and closeness and betweenness, and where we had already said, well, the reason why we do these things, if you remember, is very often we use this to visualize aspects of a graph, to make nodes larger or smaller, or to give them a certain coloring, and also to make the analysis, the visual analysis, if you're a human exploring a graph, to also make that a bit easier. And on the other hand, also the fact that we can quantify the importance of certain nodes typically in a social network, for instance, where does gossip spread from, or who has a lot of friends, or who are key infrastructure components in a social network, from a socionomic perspective, that can also be interesting to look at. And then we said, okay, at the end, what you can also do is you can take these metrics and probably already have some features about your nodes. So you can think of it as already kind of an introduction to a featureization approach as well, where you try to extract some aspects from the social network topology and bring them to the node level together with those static attributes that you have, like the age of the customer and the promotions that they have and so on and so on. And then we made a small sidestep to community mining, where we said, well, you can think of this as clustering on top of a graph layout or a graph topology, and where we had already seen two very basic techniques, if you remember, one being based on optimization, trying to find a cut, and the other using that metric of betweenness, but then on the edge level rather than the node level, to basically decompose a connected network into completely disconnected components until the very end where every node is in their own little group. And then similar to hierarchical clustering that we saw before, you typically would end up somewhere in the middle to pick your communities. But we also said, well, the drawback of both of these techniques is that this is extremely computationally inefficient. Both betweenness is difficult to calculate, but also tackling this as an optimization problem to find a minimum cut. In larger networks, this becomes very unwieldy. And this links back to the hierarchical clustering approaches, where I also said there, well, divisive approaches, they do not exist with classical tabular data because it would be way too computationally expensive. So the alternative would then be, since this is top-down, is you start from the whole graph and you try to decompose it, is maybe also try to find an alternative view where you do it bottom-up, where you start from the assumption, okay, every node that I have in my graph, let's pretend that they are in their own little cluster or their own little community in this case, and let me try to figure out stepwise who I should join together, which of the nodes that I can join together. And again, not using kind of feature distance similarity as you would do in classical clustering, but here, since we only have the topology at a basic level to work with, also here based on the edges that we find between nodes, because in clusters or in communities, we expect there to be a dense linkage of edges, and between communities, we don't want to have too many edges in between. And indeed, such approaches exist, and already said last time that the Louvain algorithm from colleagues here, already pretty old by now, but which is such an approach that works bottom-up, that tries to start from the assumption that each node is in its own community, and then greedily tries to join nodes together and to bring them in their own community, in their own cluster by merging them bottom-up. And the way how it does so, and that's a little bit, or the details are not so important, but the basic idea is for every node, and at the start, every node is in their own little cluster, is you decide who should I merge, or which of the existing communities should I merge together. And you do that based on what gives me the highest increase in for some metric. And that metric is called modularity. So for every potential merger that I can make, I calculate how much it would increase the modularity, and then the one that gives me the highest increase is the one that I will go for. And modularity then is a metric basically that gives me some idea of the quality of a division of a graph into communities. So it's the relative density of edges, because again, I can't assume that I have features here for my nodes. I only have the graph topology, so it's a measure of, or relative measures of edges within the communities or inside the communities versus edges that cross communities. And again, the idea is that you would like to have as many edges as possible that stay in a community rather than having edges that cross communities. Again, within a community, we would like there to be a dense linkage, everybody connected to one another, but across communities, we don't want there to be too many links. And that's a bottom-up approach. And there are other bottom-up approaches like this as well. You can figure something out that works clique-based, and a clique in a graph is not something that itself has to do with community mining. It's more of a general kind of construct, but you can use it to perform community mining as well. So a clique is a part of your graph, so is a subgraph where every node is connected to every other node in that clique. And of course, the more members that you want to find that are part of that clique, the harder it will be to find such a clique, because you're kind of imposing, okay, if I take 3 nodes, then they're all connected to each other. That's still doable. If I go to 4, 5, 6, 7, everybody being connected to everybody else, that will typically be harder to find. So typically what we then look for is, I will try to extract the maximal cliques that I can find in a graph. So what's the largest clique? The clique consisting of the largest number of members, where still every member of that clique is connected to everybody else in that clique. But again, this is not so simple to calculate, right? So this is a computationally expensive process, so it's maybe also not optimal to then use this as a community mining technique, but it's again something where you could work bottom up. Now, if you want to then take this into a community mining approach, well, then you know that a perfect clique where everybody is connected to everybody else, that this will be pretty rare. So you can say, maybe I'm not looking for a perfect clique, I will set some form of a threshold, a less stringent alternative, a near perfect clique, right? Using whatever kind of relaxation that you can think of, you could say, well, a K-core clique is a clique where every vertex is connected to at least k others in the subset. And then you can express that in relative terms. So you could say, well, an 80% core clique is a clique where I, for instance, have 10 members in it, but each of those 10 members should only be connected to maybe 8 of the others, right? Instead of all the 9 others, or all 7 of the others. So where you don't have a fully dense connection, but it's something that almost looks perfect or almost looks fully connected to each other. And then this gives you a potential to do bottom-up community mining with this as well, because you can start with again, putting every node in their own community, and then growing the communities out as long as the near perfect clique relationship gets maintained, right? And then until you stop and you say, okay, I cannot add anyone further to this community that I have, because that would break the clique construct that I have on top of here. But you can see within the communities that I have, that I still have a dense linkage between the members. And the benefit of this approach, or why this approach is interesting to take a look at least, is because this also shows that potentially you could even say that as you grow these cliques out, that you can have members in your social network that are maybe not just part of a single community, but that are part of multiple communities as well. And in some cases, doing community mining where members can be part of multiple communities can also be interesting. And I also mentioned that before, depending on the community mining technique that you would pick, either it has support for such overlapping communities or it does not. And if you want such a support, of course, depends on the style of the analysis that you would like to do. In some cases, and again, if we make the link to a more broader featureization approach, of course, this is very unsupervised. But again, if you think more of using this in a supervised pipeline, just as we did for clustering, for instance, here too, we could say, well, then based on these insights that you find by these communities or these cliques that you're forming, you can think of features to generate from that as well. Like, okay, in your community, how large is the community that you are in? Or in the case of overlapping communities, how many communities are you a member of? Those are also descriptive features that we can then generate from this that might end up being helpful or not helpful in relation to the target that we're then trying to predict for all of these nodes. But that was the same with k-means clustering as well. Same here, the challenge typically is, but we'll come back to that, I already mentioned that I think last time as well, that of course here too you need to set this up in a way where it is repeatable for new unseen test instances as well. Whatever you do in this kind of featureization pipeline, once you go predictive, you need to make sure that you can also apply it on unseen test cases. And for graphs, as we'll see, that can be a little bit tricky as well. Now, there are many others or other methods that are available in community mining, so this is just kind of a very brief overview. Again, in terms of applications, very often if you think about predictive techniques, we will use this as, again, an alternative for feature generation, but on its own, again, it's used for like viral marketing or to do targeted marketing or to stop the viral effects of churn, for instance, that's going on, or to do a sort of a segmentation analysis, but from a social network perspective, like, okay, who are the members of your community, and then what do those people look like, or what identifies your community, basically, and can we also then construct profiles based on that information rather than the traditional feature-based approach, but also use the topology of your connections. Or at the end, use those community labels or information of those communities as extra features in a predictive pipeline as well. So a whole lot of the story that we're doing so far, and that's a traditional approach, is trying to come up with featureization approaches that we can then plug into our standard predictive pipeline to predict some target, typically by node, or a target by node. So then we can discuss, or we can think of, okay, which other featureization approaches are out there that I could apply. Again, I have here this graph that I could utilize. Of course, the main thing that the graph enters is, again, typically you come from a situation where the nodes or the bulk of the information carrying aspect in that graph, meaning that typically you already have features for the nodes. Also, the targets typically are defined for the nodes. So what the graph enters or adds extra is perhaps features on the edges, right? But typically that's only a weight, or maybe not even that. It's quite rare to have features on edges, but you might have that. But also the edges themselves, so the topology of the connections themselves is something that you would like to extract or convert to the level of those nodes to then improve your predictive learner's performance on that, or your model's performance. So that's our common assumption. Once we will talk about graph neural networks a little bit, this is an assumption that we will be able to break. But if you stick with the more traditional approaches, this is the common assumption. And very often, the usage of graphs is set up in such a way that we say, okay, the nodes are the most interesting aspects in this thing. So it's my nodes, which are my customers or my claims and so on, that will carry the labels. And very often that will hence be positive or will be negative. Not always. Sometimes it's about the edges, the fact that a transaction, for instance, between two parties, whether the transaction is fraudulent or not. But in the majority of cases where you end up using a more traditional approach, very often it will be assumed that the nodes carry the class labels. And then you can think classically, if you look at literature, okay, and let's say that now you're in this situation, you have your graph topology, you have nodes that you have given a label. Already there, we do need to be a little bit careful, because if we think of churn, for instance, or the spread of a virus, very often the label, or if you want to set it up correctly at least, the label is something that will happen in the future. Right? So we do need to be a little bit careful, even if we do not assume information coming from any feature yet, but we only use the topology of the network itself. We need to be a little bit careful. And hence, if you read, and very often in papers, it's done incorrectly. So the idea here of this picture is that very often, or we basically have no other choice, is we want to test using an out-of-time test. It's not that we can really cut our graph itself in a train and a test split, or a train validation and test split, because then we cut right through the connections. So typically that's not something that we want to do. So the only choice is to test using an out-of-time approach. And then very often, if you look at spread of churn or spread of fraud or spread of a virus even, what you have is you have some historical information. And you have information very often, and here you see both blue nodes, red nodes, and white nodes. Very often the information that you have will be red only, meaning what are the nodes that have already churned from me? Like in the telco example that I showed previously, who are the nodes that already decided to leave me? In the case of a virus, who are the nodes that have already become infected? In the case of fraud, who are the nodes that have already done something fraudulent in the past? That's not really a label, right? That's actually a feature that you have if you think about it, because that's something that you already know now, right? You're not interested to predict the guys that have already churned, right? Those already lost. Maybe you can predict if you can get them back. That could be another question. But in the case of traditional fraud, churn, virus infection, if it has already happened, that's a feature, right? That's not a label. What you're interested in, and maybe you have cases like the example here, but that's more rare, where you know for a fact that they are negative. Right? With virus spread, sometimes it happens like you have already been infected, but you got better, so you have immunity, for instance. That's typically the model then, susceptible, infected, and recovered, SIR style of models. Typically there you find those negative cases as well. That's also something that you know from the past, right? So it's also a feature, like you're negative because you got immunity, or because we know for a fact that you will never be fraudulent, or you will never leave me, for instance, in this graph. So hence there it's a bit less common. Or maybe we already did a check on you in the case of fraud, but we found out that nothing was wrong. So you might also have some historical negative evidence as well. But in both cases, those are not part of your labels. Right? And you will also not really care how well your model does in terms of predicting these, because you already know those nodes. So the ones that you care about to predict correctly going forward are the white ones, or the ones where you're still unsure about. Like in the spread of fraud, or in the spread of this virus, or in the spread of churn, out of all these white ones that so far, up until today, look like negatives as well, they haven't churned yet, they haven't become infected yet, they didn't commit any fraud yet that I know of, right? But who is most susceptible at risk, right? That's that's my label. And then typically the way how you do that is, well, that's why you need to track your graph over time, because you will have to observe these nodes for a while and then checking, okay, which of these guys is going to turn red or is going to turn blue, but mainly it's the red part, the positive part that spreads, and that's the thing that I want to predict. So it's no use trying to predict something that has already happened, right? And again, you can find papers where they set it up in the complete incorrect way. But the fact that something that you have already churned, that's not a predictive task, that's a feature that you have. And the predictive task is you want to know how that will spread going forward to the nodes that are currently still with you and still have a contract going on with you. Now, saying that we do set this up correctly, we can think of different approaches to tackle this. And one approach says, well, if this is the only thing that you have the network structure and you have a bit of historical information about who has already left before and who is negative, who is positive, and you're kind of wondering, okay, if I let this time line play out for a little bit further, like this white one, what's the probability that they will become positive or negative in the next time step? How do I do that? And I don't have any other information. So the only thing I can use is the network structure. And what I'm basically looking for is I want to build some sort of a simulation tool at the end of the day. Like, okay, I have nodes that have already become infected and were healed. Simulate me the further progress of this infection, basically, that I'm modeling here. And then if I know this over time, I can use it as a probability to predict your risk score, basically. Now, it becomes more interesting if, in the case where I do have some other features of these nodes as well, which we typically have, and I say, well, I still would like to utilize those, and I have already all of them in my XGBoost model. What I would like to extract from this network structure is give me additional features that rely on that topology that I can mix in with the rest. And we have already seen a couple of examples, like these social network metrics, like betweenness and closeness, they fall into that category. Of course, the dream would be is, why don't you just use the graph in its raw form as is, with all the features that you have for the nodes, and potentially the edges, and potentially the global ones for the whole graph, and you build something that can do all at the same time. And traditionally, that's the thing that's been a bit hard, and why graph neural networks can aid us a bit in that sense, because they are capable to handle that. Not always easy to set up, as we will see, but we'll start with the traditional approaches first. So we'll start with number one, use the network structure, and we don't assume any other features yet. So we only have that topology, and we have some historical information. So our goal is we want to infer the class, positive, negative, for instance, in the case of a binary setting, for unknown nodes. Whether that is fraud or churn or survival rate or whatever. It can even be like a regression target if we would like to have that spread around. Might be a bit harder than a positive-negative target, but this is the core idea. Like, I would like to simulate some spread of infection, if you will, or rumors in my network, and then seeing what happens. And now, of course, the difficult part is that, yeah, how do you set up a simulation correctly? It's a bit of a catch-22, right? You can kind of feel that for a node in the middle here, yeah, it's susceptible because it's directly connected to some positive nodes, but it's also connected to some negative nodes. And maybe if I have connections like here, where I have a lot of unknown nodes that are together and are linked with one another, if the first one is connected heavily to red nodes, then that one will also end up infecting another unknown one. So there is a back and forth effect that goes on. So how do I take these cyclical effects, these back and forths, correctly into account so that I can converge to something that looks reasonable and looks correct if I simulate kind of the spread of these classes in there? And a lot of, especially, well, initial techniques, they said, well, maybe there is a way how we can simplify this a bit. And the simplification comes in what is described as the Markov property. And the Markov property says that, at least for one time step, to simulate one time step, that every node's outcome is only determined based on its direct neighbors. And then you can make things very simple. Then I only need to look at your direct neighbors, I calculate some ratio of positive versus negative, and I use that maybe to assign you a class label. That's an easy simplification. We can wonder about whether this is workable or not. It also sounds a bit too easy on paper, but the interesting aspect will then be that, okay, but we don't do this once. If we then take this property and we simulate it for many time steps, then maybe some overall convergence will appear as well. Now, even this simplified approach, you can wonder about, well, is this actually true or not? If I look at any social network of humans, is it indeed the case? And even from a predictive perspective, we can generally ask the question, or we could wonder a little bit about, well, let's say that I want to predict something about you in your social network, and even I have features or not, that doesn't even matter, but let's say, would it be sufficient that I only give information of your direct connections? Or do I need to look further than that? And is it completely insufficient to do that? And this has been studied to see whether there is already information in your direct connections, whether this would be sufficient. And this has been studied, and this has been denoted as the concept of homophily. And basically what this means, or how this is described, is, well, people have a tendency to associate and to form connections with people that not only they perceive to be similar to them, but also simply are similar to them. And that's the case if you look at, for instance, economic or financial aspects, so income, for instance. That's the case if you look at hobbies, for instance. Even you could wonder, if you look more at fraud-based approaches, is it then still the case that we find these connections between fraudsters, averagely speaking, more than between fraudsters and non-fraudsters? So this has been tested. There is a way how you can easily calculate this. Like, let's say that I have my two classes, positive, negative, so I'm in my binary classification setting here. And what I would expect is I have a group of blue people here, I have a group of green people here, maybe one or a group is the fraudsters or the churners, the other ones are not. If homophily would hold, so if that principle would be correct, what I expect to see on average is to find more links between members that have the same class, so between blue and blue or between green and green, compared to if these connections would be completely random. And what I also expect to see is to find less links between members of a different class, so less links between blue and green in this case, then I would expect to see if the connections would be completely random. So I compare what I observe here with what happens if I would just randomly distribute connections. Do I see more links between members of the same class? Do I see less links between members of the opposite class? And if that is indeed the case, then I have evidence for homophily. So what do we observe? Well, this has been tested, like I said, and even in cases like fraud, for instance, if you look at graphs that you extract from there and you perform this test, then indeed you have evidence, not large evidence. It's not like every fraudster talks to every other fraudster, for instance, but you do have evidence that on average there are more connections between fraudsters, for instance, than you would expect in a random configuration. And it's not because they really want this, but sometimes it's unavoidable because they use each other's resources or they use shared resources. Like, remember the case of the credit cards that are utilized in the same store. That's not fraudsters that directly connect with each other and make a plan saying, let's go to the same store. That's just because the behavioral tendencies are similar and hence these connections start to form. Similar in churn. There you also find evidence for the same thing, that indeed it's pretty likely that if there are customers that have strong connections to customers that have recently churned, that they will also follow suit. So also an evidence for homophily here. So this is all evidence to kind of say, yes, indeed, this graph topology does contain information that we can exploit to predict something about those nodes going forward in the future. Finance or economy, this is an older study that was done by taking a look at a call detail record graph from a telco provider and then matching that with income of both the one that made the call and the person that received the call. And what do you find? Well, there is a clear diagonal line in here that typically the way how we call and contact people in our friends network or colleagues network or whatever, anybody that we call to, we tend to mainly call with people that fall into the same income level as we do. And we typically also get called by people that fall in the same income level as we do. So also evidence for homophily. So indeed, this homophily aspect does seem to be a valid assumption in many settings. So that's good news. That means that we don't need to have some kind of all-powerful knowledge about the full graph, but we can already extract a lot of information by looking at your direct connections. So, and that's then the idea of network-based inference. We don't have any features. The idea is as follows. I have some known historical, and I call them fraud, non-fraud here, but again, it could be anything. I have some historical labels that I know things that have already happened or I have evidence for, and I try to spread this to the unknowns. So that's the common case. You have the negatives typically you don't have. In the most cases, what you do have are some known historical positives. These are the nodes that have already churned or have already committed some fraud. You do not really have evidence for negative aspects, except for maybe viral cases because you recovered and you're immune. But typically in business settings, you have some known positives, and you assume that all the others are unknowns, basically. So you only have red nodes. And then you want to figure out, okay, how will these red nodes spread their influence in this graph over time? Is it this node that will be infected first or churn first, or is it this one? You want to assign some probabilities on that. Now, the early attempts, because of this Markov property, yeah, there is papers written about this, but don't get too excited or crazy. The idea of, oh, we're going to set up some sort of simulation sounds fancy on paper. Yeah, this does nothing, obviously, right? So this is called the relational neighbor classifier and simply says, okay, then for every unknown node that you have, look at its Markov neighborhood, look at its direct neighbors, its direct friends, and then you see that there are 2 known positives there, that there are 3 known negatives there. So your risk of also being a positive is 2 out of 5. Yeah, that's not very revealing, right? And then you can also, and typically the larger claim or the complaint will be, okay, but what if you have nodes that do not have any known connections and that are only connected to other unknown nodes as well? Then what do I do, right? And this wouldn't work. I can't basically assign you any score. But this is the basic building block. And the idea is then to go from this to something that more richly simulates spread or simulates propagation over time, is that you basically apply this trick, but multiple times. And you set up your simulation that way. And then you come to what is called propagation-based technique. So they do exactly this. They say, okay, for every node, we look at its direct neighborhood. We use that to assign some score to the current node, but then we let that run for a couple of times. We go through 1,000 iterations and so on, and we utilize this approach. And there have been many kind of ideas that have been developed to do this. We'll see a couple of them, or the most important one. But basically things such as Gibbs sampling, iterative classification. I don't think that I have the full explanation anymore on the slide. But basically what they do, and you can see a bit the figures, is, okay, for every node that I have in my original graph, check the Markov property, assign a probability to that node, but then don't stop there. Also spread that further and have nodes flip a couple of times or allow them to flip from negative to positive and keep track of statistics over 100 rounds or 1,000 rounds of iterations, and then you use that to decide upon some final score. And then you get something that looks more like, instead of a single shot, looks more like something that propagates throughout a whole network. So the same goal as these relational learners, but now over multiple time steps. Now, the most important one, and that's the one that we discuss here, the most by now used one to kind of model propagation is something called personalized PageRank. And it's exactly the same as the PageRank metric that we saw last week. Remember our example with the websites, with the matrix multiplication, and where I said, well, if everything goes well, this will converge into some eigenvalue score for each of the nodes to kind of indicate how important that they are. And I also mentioned at that time that the whole kind of idea of Google at the time was that since this doesn't converge and because this doesn't scale well to large graphs, is that they took a random Walker-based approach. And where we said, okay, you have a network of websites, you drop a web surfer randomly somewhere and you let them start from a particular website, and as they are walking around, they're clicking links, they take a piece of importance from the source and they drop it off at the target. And at every step you check, are you tired? Do you want to stop surfing? And then you repeat it again. And then the benefit of this is that you can do this in parallel. You can spawn a whole bunch of surfers in a network and have them walk around. Personalized PageRank is exactly the same thing. If you check out the link, you will see this animate, right? So, but with the difference that when you decide to drop a surfer and you let them start randomly somewhere, that you change that. And you say, okay, I'm not going to drop you with the same percentage starting from any of these nodes. I'm going to change that restart or that start distribution of probabilities or weights also a little bit. And in the case of personalized PageRank and the way how we use it here to model propagation is typically the setting where we say, well, very often you have historical information about positives that already happened. Nodes that have already churned, things that have already committed fraud, nodes that already got infected. So every time you drop a random walker in this graph to start and move around, you only let them start from the known positives, from the historical positives, the things that have already been infected, if you will. And you let them walk from there. And so in this case, in the extreme example where you only have one person that has already been infected by, say, the hantavirus, right? We let our server start from this node, and as they walk around, they take a piece of this node's importance and will spread it around in the connected nodes. And other than that, we apply the same strategy. Every step we check, well, are you tired? Do you want to stop? So, of course, the nodes that are further away from this source node will be less under the influence of that infection. And this is a very easy to set up way to model spread, to model the propagation of something of a historical positive, and then that's the main or the favorite way to model propagation nowadays, and works pretty well. So this is what the example, I know it's a bit hard to see, but the red nodes here are the ones that have already been infected or already positive, and then from there, here you can see, well, the ones that are kind of these, this darkish red color are more at risk, and the black nodes at the edges, well, they didn't feel the influence of the infection yet because they're too far away. It's too hard to reach those nodes coming from these red nodes. There are other approaches as well to do this sort of label propagation, because then that's what we are basically doing. You start from some known labels and you try to spread them around. There is also a paper called Learning from Labeled and Unlabeled Data with Label Propagation, which is very similar. The benefit that it has is that it's a little bit easier to also set this up in the case where you do have historical information both for positive and negative classes, or even in the multi-class setting. So if you would be working with known historical binary labels or even multi-class labels, you can utilize this to model the spread or the propagation of them as well. Again, the left-hand side is what you start from. Same question or same situation. The black nodes are my unknowns that I want to check. You let this spread around, and if you let this run all the way, this would be the end situation that you end up with. But of course, because you have this time effect, you can kind of give a probability to all of these nodes, telling you, okay, how soon will they become infected, or hence, what's their score of being at risk. There are other propagation-based techniques. Pretty fun to play with these because you can kind of simulate spread and so on, or simulate the spread of fraud or churn. It's not always straightforward to getting these techniques to converge. So even for these kind of simulation-based approaches, sometimes your graph will collapse quickly in a situation where everything suddenly becomes positive or everything suddenly becomes negative. So depending on the technique that you use, you will have to tune a bit the hyperparameters that are involved with that. That's also what makes personalized PageRank pretty favored in practice, because this tends to work quite well out of the box. Earlier techniques such as Gibbs sampling and iterative classification very often explode into something that does not converge at all. So that's also something to be a bit aware of. And regression propagation, if your labels would not be binary labels, but they would be numerical ones, for instance, also there it's a little bit harder to find good techniques that converge well, as you can imagine, because then you're talking about a graph where the start situation are some known continuous values, and you want to know how these values spread around in your graph. It's a bit harder to set up as well. So that's one way. If you would set that up, so you have your network topology, you are in the situation where, fine, I have some nodes that have already churned in the past, and I have some nodes that will never churn because they're my best customers. But for a node here, I would like to know, okay, give me the probability that you're at risk. And based on only the topology, I have nothing else that I need here. I don't have any other feature, just some historical labels that I have observed, and I want to model the spread based on this. So that's one approach. That's the more rare one, because typically you do have features for your nodes as well. And basically, you're still looking, I don't want to use this. I would prefer to still use my logistic regression or my XGBoost or my random forest, but how can I then extract some features from this graph topology and bring them in there as well? So that's the second class of techniques. And since we're wondering about this, or anyway, since we're discussing about this, what you might also say, well, given the fact that you probably do have static features of these nodes as well, you don't lose what you did here, right? If you use personalized PageRank or something like this to give you risk scores for all of these black nodes, just use those scores as a feature then in your XGBoost setup, right? Instead of using them as a direct prediction, just use them as a feature as well, right? And indeed, that will be the common scenario where you will then often end up with, is that you will not use this as your final prediction method, but you will use this as yet another feature that can inform your overall predictive pipeline. So indeed, and also the features that we did previously, coming from closeness, betweenness, degree, I also think about those as adding those in as features as well. And if you play with community mining, like I said, you can also think about extracting features from there and also adding those in. So indeed, that is the overall of the most commonly applied approach. And then the question is, what other type of features that we could extract from a graph topology can we then think of that might be interesting to an overall predictive setup? And this was first described, or the most well-known description of this approach is called relational logistic regression. From 2003, where they had exactly this idea, and they said, well, very often your nodes, you already have features for those. You already know the age, the income, recency, frequency, monetary values, and we're going to extract from the network. Here we give you some ideas of things that you can do, right? You extract the most frequently occurring class of the neighbor, the frequency of the classes, the binary indicators, and so on, and then you just use this as features in a single logistic regression model. Cool name, but it doesn't have to be a logistic regression model. It doesn't matter what it is. It can be XGBoost, can be random forest. Basically, it's a guideline, or what this paper did is it gave some templates of extracting features from a graph that you can then use in any supervised setup. And not even a perfect pipeline, because a thing that it basically failed to realize well enough is the fact that if you try to extract features from a graph, but you do it by, for instance, looking at the most frequently occurring class of the neighbor, that you're kind of introducing data leakage again there. It's okay if you look at historical classes, as I have been emphasizing so far, where kind of your starting point is something like this, where you say, okay, for some of my nodes, I already know what they are. But if you would look kind of at the end result, something like this with the true values, let's say, and you would use this to featureize, well, you're looking at something that you're not supposed to look at, right? You're using the labels directly to featureize, and then you can't really get away by the fact of saying, oh yeah, but I don't use the label of the node itself, I only look at your neighbors. Yeah, but still you have data leakage, right? So we do need to be a little bit careful here. In order, it's okay to set up the features or to extract features from a graph, but we do need to make sure that we do not introduce data leakage there. So this was their kind of original approach, saying, okay, you have a node in the middle here, and if you already have some basic features like the age, the income, and so on, you know what? Take a look at their neighbors and also use as a feature the number of neighbors that are negative, the number of neighbors that are positive, and so on. Both binary and using a count, and what is the most occurring neighbor, all good and well. But again, please, this then should assume that these neighbors and these labels here, that these are historical labels, that this is actually a feature, something that has happened already. If you do this in kind of the original intent that they describe here, you would look at the actual labels of these neighbors, you don't know, eh? You're introducing a perfect form of feature leakage or label leakage in this case. So do a bit, or be a bit careful if you utilize something like this. It's fine that you say, okay, I already know the guys that have committed fraud already. That's a feature, and that you can propagate, and that you can use to featureize, but not the true labels, and not something that will happen in the future, right? So be very careful again with your labeling strategy on top of graphs, right? And don't do that incorrectly. Crazy that, yeah, some papers made a mistake on this, but yeah, it happens. Now, the insight itself is good, of course, and what it does, what you can do, is instead of focusing so heavily on what are the labels of these neighbors that I'm actually not supposed to look at, what you do know is, of course, you do know the features of those neighbors at the time of constructing your feature vector. You do know the features of the node itself, but you can indeed look at the features of the nodes that you're connected to. And then you can think about, okay, how about for every, if I need to bring that back at the level of a individual instance, indeed I know your age, I know your average duration that you spend in my shop, the average revenue that you give me, the promotions that you have. I can, in fact, look at your friends that you're connected to, or your friends of friends, and I can also take the average of their age, for instance, and bring that in as a feature. Will that be helpful? Well, maybe. It might be informative to say, well, how much does your age differ from your direct friends, for instance? Maybe in the case of fraud, who knows, right? It's something that we can add in, and then we can utilize our model to tell us, and we can use things like Shapley values to then tell us if these features are informative or not. So we are free to look at the features of the nodes that someone is connected to, and not just of the direct friends, but potentially also the friends of friends and so on. And then we can combine this with social network metrics and potentially also smart ideas, right? So what we could do is a setup where we say, for every node that we have here, I'm free to use as a feature the degree of those nodes, right? And again here, if I do use labels to also say something about, well, are you connected to, or what's your fraudulent degree, meaning to how many fraudulent nodes are you connected to, that I do, again, take care to assume that if we say fraudulent here, so these 4 black nodes that we have, that this is already fraud that happened in the past, right? I'm not using the labels to do this. I'm using information that I already know. So same for the case of churn. These black nodes here would be ones that have already churned. Right? And that I'm free to use because that I know, but I don't look at what will happen in the future. So again, this is a situation where I assume that these black nodes have already churned or already have been spotted to commit fraud. And for all the others, the white ones, well, those are the ones that I do not know yet. And I would like to predict what's going to happen in the future for these white ones. So I can use their features, I can extract degree, like is illustrated here. I can also count triangles, which is also something, or something that's oftentimes done. I can count, okay, for this node, how many triangles are you involved in? And out of these triangles, how many of these are fully fraudulent versus semi-fraudulent versus fully legit? Very often, these kind of triangle topology-based extractions can also end up being helpful as a feature for a predictive model. I'm throwing away the full information of my network. That's something that I have to live with. So all of these approaches are ways to retain or to encode or to represent or to embed some of this topology that I have in this richer structure in a feature vector, basically. So again, I'm trying to find a representation of every node in this graph in a manual way. I can also look at what's the shortest path between you and your closest known fraudulent node, for instance, and also add that in as a feature. And then you can look at hop paths, like, okay, how many paths do there exist between you and a fraudulent node? In the case of A, how many one-hop paths? So only one, from A to I, that's one hop. In the case of B, also only one, right? And in the others, maybe 0, sometimes maybe more. How many two-hop paths exist between you and a fraudulent node? How many three-hop paths? And then the metrics that we discussed previously, calculate a measure of closeness, calculate a measure of betweenness. Who knows, maybe this is a good feature that will help to provide some information about your overall importance in this graph. And then, as we discussed previously, you know what, also run PageRank or personalized PageRank in our case, and let it start from the known fraudulent nodes, let it spread its influence, and then the PageRank score that you end up with, which normally you would have used as a direct probability of risk, let's say, well, now you just use as any other feature in your feature vector. And once you're done with kind of crunching to your whole graph like this, you give this whole bunch of features to your XGBoost approach, and you hope that your results improve, right? On top of not using the graph at all. And that's kind of, or for a very long time, this was the standard approach that was followed in data science scientist teams in organizations. When they wanted to include some graph info or some social network info, this is the way how it was done. So the nodes are the label and the attribute carriers. We keep our network simple, non-directional, domain-driven features, and then personalized PageRank is typically a feature that's pretty good at capturing kind of global risk, let's say, because this propagation effect is pretty strong in there. That's basically the only feature that allows us to look at the network a bit further than the EagleNet or the Friends of Friends net, but also more the global spread of this positive historical information that we have there. Now that's all well and good. I already mentioned, be very careful that you do not introduce data leakage by doing any of this sort of featureization and assuming that you can look at the actual labels of the nodes, right? Don't look at the future, right? You can look at what has already happened in the past, but don't look at the thing you're actually trying to predict and use that to featureize from, right? So be very careful in setting that up. But if you do this, okay, then that's fine. Still should be careful to validate. Like if you do this incorrectly, obviously, and you might end up with, I use some information coming from my graph, and suddenly my ROC curve is completely perfect. You kind of know that you're in trouble, right? You probably can feel that there is some kind of leakage that happened there by utilizing your graph structure. So also here, if we want to keep ourselves honest, we would say, or we have to say, okay, look, even given the fact that we do not featureize using the labels and so on, and we only do that using historical information, I still need to make sure that I can test out all of these featureization steps that I'm doing on unseen data. So also here, I should make sure that this happens after I construct my train and my test split. Train on the train, then reapply everything on test. That's okay, but because we are doing some featureization from our graph, even although we might not even look at the labels at all, but even the fact that we featureize using the graph topology, also there we have some form of data leakage, especially if we have the same graph for the train and for the test set of instances. Well, obviously, right? And you bring information over from train to test. And then the question is, okay, how can we fix this? Because labeling of nodes will differ over time if we extract different graphs over time, and also the graph topology itself might change as well. There might be edges that appear or disappear. There might be nodes that enter the graph or that get removed from this graph. So this kind of indicates that, well, if we apply here the same in-sample approach of splitting, where we say, okay, fine, then take your whole data set and 20% you make part of the test set, that this wouldn't really work simply because of the fact that also for your graph, you would have to break it up into two pieces and say, well, this is my train graph and this is my test graph. Your feature generation will break because you're cutting right across the connections that are between your nodes. And this is the whole reason, or this is the whole kind of setup where the only typically viable approach to set this up is to work in an out-of-time test setting, where you say, okay, I have my train set of nodes, I take a look at the graph as it is then, I featureize from that, and then when it's time for testing, I take a look at all the instances that I have with their test features at test time, and I look at the graph as it is at that moment, and I apply the same featureization tactic or strategies that I have developed on my train set. It's not perfect because, of course, if you think about your typical graph of customers calling each other, let's say you try to predict churn, and for your train graph, you look at the 1st of January 2025, for instance, and you look a bit forward to see who will churn in a few months from now. You take a snapshot, you construct a graph, you think about clever featureization techniques, then you test it out, you take a look at your customer base 1st January 2026, you also construct a graph there, you reapply it, it works well. But for the most part, that graph of 2026 and 2025 will still have similarities, obviously, right? Which is fine. If those similarities are there, then it's also okay to test on them. But there is, of course, some overlap in the connections between your instances that will stay or that will be retained. So that's the preferred approach. Very often, if you especially look at literature on graph neural networks, they will make a difference between what they call inductive learning and transductive learning. What I've just described, where you construct your graph at two moments in time, and you apply or you train on the train graph, and then you test out your approach on the test graph, that's the inductive setting. So in the inductive setting, the idea is that you have both a train version of your graph and a test version of your graph. Typically, because the nature of business is such that typically then what we mean, or the way how it's done, is that this train graph and that test graph are at 2 moments in time, extracted at 2 moments in time. That's the most, let's say, robust approach. Now, in a lot of benchmark settings, or in a lot of kind of experiments that people do in practice, or if you're a researcher trying to come up with some graph learning technique, there aren't a lot of graphs available where you both have a train version and a test version extracted at 2 moments in time. In industry, if you work in an organization and you have a graph database, you will be able to do that. But sadly, a lot of publicly available graphs, we don't have a train version and a test version. In a lot of kind of social networks that people have extracted, or they have asked questions to people, or they go to a university campus and ask, who are you in a relationship with at this moment, and things like that, you only have a single graph. And what is done instead is, it's kind of like this approach then, that's called a transductive setting, where, and for graph neural networks, for instance, where it's then said, okay, then take out a fraction of the nodes that you have in that graph and mask them, hide their label, right? And during the training, you will train to make a prediction for all of these nodes, but you will only evaluate your approach for the ones that have question marks here, that you have masked, and see how well your model is doing based on that. That's okay, indeed, then at least let's say that you, and we will immediately see how this works. So you have masked one of the nodes and you have neighbors that you have not masked, and hence that carry a positive or a negative or also a question mark signal. Again, you should then think carefully of, okay, what can this model that is trying to make a prediction for this node in the middle here, what can it utilize, right? Can it utilize features that come from these neighbors, like their vector x? Well, yeah, sure. We can assume that we know the features of these nodes. That's a snapshot that we took of them, of these customers. So if I want to make a prediction about what you are going to be, I can use the features of your friends. I can, of course, also use your own features, like I would normally do, right? And I evaluate using your own known target, right? Which I hide, I won't use. That's the thing I'm actually trying to predict the probability for. Can I use the labels of these neighbors that I have not masked? Can I use the fact that, I know that you're a positive and I know that you're a negative? Debatable, eh? If you do, then you really assume that you're working in a setting where that information, during training, that you actually know those labels of those neighbors. And again, if this is something that has already happened historically, then it's fine. Generally speaking, really can't, right? If you make a train test split and you would featureize in such a way where, for an instance in your train set, you look at the labels of other instances, generally we say, well, that's not done, right? You can't. So I can't pass information of the known labels of these guys to predict something about you. So that's hidden as well. I don't do that. But features I can. So if I would set it up in this way, is it then completely solved, right? It's kind of comparable, whatever model we use here, this is a bit comparable to saying, okay, use this featureization technique, like the thing that you did over here, and you look at the average age of your friends and which promotions your friends have, and maybe you use a bit of the topology there, and let's forget about the fact that we already have some historically known positives there. We only use features and we use a bit of topology, and that's it, and then we're done. So in that case, or we save them. Well, not fully yet, right? The thing, we're relatively safe, but the thing then that we do not test on, if we then ask our model, okay, please predict the probability that this node is going to be a positive one, and we're going to compare that with the true target, and we'll calculate some loss value, and we try to get it down as much as possible. The only thing that we haven't really tested for in that setting are changes of the topology of the graph itself. And if you do have a train and a test graph over time, then you can at least also test on changes of the topology. Let's imagine that for some reason, your graph is pretty volatile and connections change rapidly, and also the way how people connect change rapidly. Maybe on average, maybe this month people have 5 friends, but then something happens and now they have 10 on average. Or the way how they connect with each other is different. Here, because you keep your graph topology the same, you don't test that out, you don't evaluate on that, you will not really see those issues if they would be there, because you didn't test on them. Of course, the counter-argument would be, yeah, but how much does it really happen that graph structures change so heavily that it would matter versus train and test to actually test that out? Yeah, true, that's indeed correct. But it's also about changes in terms of new nodes entering the graph, for instance, or nodes disappearing from the graph, right? So that's also part of that topology. So the only way how you can really test it out is by following an inductive strategy and having indeed a completely trained graph that you have. And then you can also mess with potentially incorrect featureization strategies, because for your test graph, again, you will be kept honest and you will have to repeat all of that again and not look at the labels there and to still be able to get a good result. But in any case, no strategy is perfect, because you will always have some degree of overlap, even if you do it inductive between your train and your test graph, even if you do try to set it up correctly. So be careful when you use knowledge of the label, right? So don't do that. Use knowledge of historical labels, then they're actually features, but not knowledge of things that still have to happen in the future. And also when you apply the model, also here, yeah, inference becomes a little bit more difficult, because that means, well, now if you want to do inference on some node, you need to make sure that you know that node's surrounding topology in the current state of the graph, right? Because you still need to re-execute these featureization pipelines. Now, this whole discussion of these pitfalls of evaluation, we did a study on this, me together with a PhD student. There have been former studies as well that try to kind of compare these transductive versus inductive strategies and kind of see the damage that not doing it inductively, how large the extent of that damage is, and the impact in terms of the learner that you're using, and that you're kind of fooling yourself in getting a better result than it's actually doing if you would really give it a new graph that it would have to work on. So inductive better, generally speaking, have a separate test graph, but not always easy in practice. So that's on validation. Now, I've already kind of been introducing or slightly going towards the aspect of graph neural networks. So we can talk a little bit about that approach, which is, so far what we had seen is, okay, fine, you stick with XGBoost, you stick with like GBM, there is this graph there. Here are all sorts of ways how you can extract features from that topology, mix them in with the features that you have for those nodes, and then run your normal predictive pipeline. You do lose some richness in terms of, yeah, you're featureizing, so you're trying to manually construct some sort of representation, but okay, fine, that's what we did with other things as well. Hopefully the learner can still get some value out of those features, like personalized PageRank and so on and so on. Now we can talk about, well, is there a way how we can directly utilize this raw structure of this graph in its raw format and have, again, a neural network construct its featureization in an automated manner, including then perhaps also learning representations for nodes, edges, or even the graph as a whole. Where this kind of, or this story finds itself in terms of where this started from comes, or is pretty much related to our story on Word2Vec. Because after Word2Vec came out, people were talking or were experimenting with the idea of what about if we use this random walker approach that personalized PageRank also does, and we walk around randomly in a graph, or maybe we can steer that walking a little bit, and we keep track of the nodes that are being visited. The node identifiers. We go from node 1 to node 2 to node 3 and back to node 2 and then to node 5. And at every step we can decide with a random chance to stop, and then our sentence is complete, and then we can generate a new sentence. That looks exactly the same as text, except that you have node identifiers instead of text tokens. And what would happen if you give this to Word2Vec and you try to find an embedding, you try to find a representation for every node in your vocabulary, and what would that look like? So that is a very early approach that was instantiated by both what is called Node2Vec and also something which is called DeepWalk. So the idea is that people are trying to find ways to construct a representation in a more automated manner, rather than you doing the manual feature engineering, but to construct a representation automatically from the network itself. So those are two early approaches. So this is deep walk. Basically, it collects short walks, and then it applies skipgram, like we saw in Word2Vec. Word2Vec itself is very, or Node2Vec rather, is very similar to this. The thing that Node2Vec adds in is it biases the random walk a little bit. It doesn't jump from node to node completely at random. It basically looks a little bit more at the topology to decide where it should walk towards. It tries to avoid revisiting nodes that it already came from, for instance. In itself, that's nice. What this kind of reveals is that, fun, if I build a for loop in Python where I can just start from a node and run around randomly, and that I have some leeway to play with that random walk also a little bit, to bias it a bit, or to maybe change it up a bit, and I can play with that, and based on that, I will get different styles of sentences or walks that I generate out of this. Same thing, at the end, I give those sentences to skipgram, so to Word2Vec, and I get a vector for each node in my graph. And potentially even more than a node, I could also decide every time I walk that I do not just give a token for each node in here, but I also give a token for each edge that I visit, for instance, as well. And then I can also get a representation for the edges in my graph. But again, nodes typically are seen as the most central thing, so very often those are the ones that we put in our vocabulary to generate representations for. And then what can we do with them? Well, you get a vector for each node. What happens if you do k-means on that vector then, and you cluster them together? Look, another idea of a community mining technique, and which actually tends to scale relatively well also to very large graphs. And you first collect a whole bunch of random walks, millions of them, then you generate representations for each of the nodes, you k-means them together, and you have your communities. And then what happens if you change your style of random walk a bit, if you make that a bit more biased or completely unbiased, would you get different results than if you cluster those things together? And indeed you can, depending on how you do your random walks, you can get clusters that match very well with the idea of community detection, so that's good news. But if you set up your random walks to behave a little bit differently, you can also prove that if you then cluster the representations for each node, that they are more linked to structural aspects, right? Here, for instance, the green nodes, or the one in the green cluster are all nodes that are key infrastructure components, potentially nodes with a high betweenness value, and the red ones are the ones that lie on the edge of the network, and the blue ones are somewhere in the middle of those two. So by steering this random walk and pushing the resulting sentences to Node2Vec or Word2Vec, because it's the same thing, and then clustering the vectors, well, those vectors, those representations indeed are capable to reveal different things about your network. Okay, fun, that's all good and well. Two drawbacks, obviously. Drawback number one is we saw the way how Word2Vec worked, and where we said, well, if tomorrow there is a new word that enters your vocabulary, you can't parametrically extract a representation for that word. You will have to retrain the whole setup, at least in the way how Word2Vec was set up. Same thing here. If tomorrow we have a new node that would enter this graph, and I would ask, okay, please now give me the vector representation for that new node, you would basically have to retrain the whole thing, and also all the representations for all the other nodes would change. So if you're looking to use this for a downstream predictive task, this is not really a usable embedding for us yet. So it indicates that we can find representations for nodes in a graph and edges and so on, but in an end-to-end kind of pipeline where we try to predict something, this is not useful yet. Yeah, and speaking of prediction, that's the second issue, is that this is completely unsupervised, right? Or semi-supervised, or self-supervised, I should say, because just like in Word2Vec, the idea is that we randomly bounce around in this graph, we make a sentence, and remember in Word2Vec, what we're trying to do is try to predict the representation of this node based on its surrounding context. So the nodes that you visited before and afterwards. That's exactly in that self-supervised setting that Word2Vec also worked in. We're trying to predict a word based on its context or the other way around. But in many cases, if I do work with graphs, it's quite likely that I do have a label that I can utilize directly. I do work with a churn graph or a fraud graph or a viral infection graph or something like that. So it would also be nicer if I can make representations that are most suitable to predict that downstream thing rather than quite general. Although general representations might also be useful, but very often I have some predictive setting in mind. So those are the drawback. So it mainly lacks the ability to generalize. I cannot easily get a representation for a new node that I would enter in this graph. And that's typically something that I would like to have. So then what's kind of the thing that I would be looking for? Well, generally speaking, what I have is, okay, I have a graph, I have topology, my nodes might have features, my edges might have features, I might have global features for the complete graph, and I'm looking for a structure, a neural network structure, as we will see, that is capable to construct automatically representations for the nodes, representations for the edges, and representations for the whole graph itself. And what I will use these representations for, again, at the end of this architectural kind of setup, as we always did, is depending on the task that I have, I could say, okay, the final then layer is take the representations for each node, pass these through a couple of densely connected MLP layers, and at the end predict a binary target. And then basically the network will have to learn end to end, okay, how do I then construct these embeddings or these representations automatically so that I'm best suited to then predict that final target. Or maybe I want to make a prediction for the graph as a whole, or maybe I want to make a prediction per edge. So that's the idea. So once I have node embeddings, the idea is then I can easily pass these to a downstream architecture to provide me with the final output. So for instance, I take a node embedding, I give this to some MLP layers, and I get my sigmoid output. Now, how do I put in or feed in the graph as an input? I have node features, edge features, global features, so that means for the graph as a whole. Typically, you only have node features, but theoretically, I can also have edge features and global features. And I have an adjacency matrix, connectivity. I need that topology description as well. The first three, we actually already know this. If we do tabular learning, just give a list of feature vectors. One list equal to the number of nodes, one list equal to the number of edges, one list with a single vector for the global ones. So those are easy. Connectivity is a bit more difficult. How do I represent that in the input side? And I could say, well, take that adjacency matrix that we saw previously and dump that in as an input. That's your input structure. Doesn't work that well to do it this way because that representation is very sparse. We saw that for a large graph, most of the elements in that matrix will be equal to 0. So if you would have to feed in or dump in this whole kind of construction on the input side, it probably will not be easy for a network to learn on. On top of that, for the same connectivity, so for the same topology, you can actually represent that by multiple adjacency matrices. So you also have some sort of redundancy there as well. So what is typically done instead is the connectivity is provided as a list of connections. Connections between the ith and the jth node, and hence every element in this list is a pair of nodes that describes the connections that I have. That's a bit of a technical detail because what this means is that if you want to develop something that can work or that can train on graph neural networks, that having ways to represent tensors in a sparse format, that this makes is a little bit tricky. But that's an implementation detail, luckily, that has been solved. Now, from a more kind of theoretical angle, we can say, okay, fine, there is on the input side, I have access, or what comes in this architecture is I have access about the node features, the edge features, the global features, and I have this connectivity information. And my goal is I want to create a representational vector for all of these elements in my graph, the graph as a whole, the nodes, and the edges. And let's say that we take a look at how would I set up a way that I can create a representation, learned end-to-end, right? So not manually. And first, we will look at the nodes, let's say. And I know that in the beginning, I have access to node features, right? So there is for every node I, you have given me a vector x with a subscript 0 because I'm at my first layer, or this is what you give me at the input side. For instance, for each node, I have the age, the income, the recency, the frequency, and so on. So I have a set of features for each node. How do I create an embedding of this per node? An embedding layer like we did with Node2Vec or previously, well, I can't here because I need to assume that in this case, I do not want to start, and this is the reason why an embedding layer can be helpful, is if you have a finite and non-changing set of elements. that you want to represent by vectors. But here I don't want this, because I want something that is flexible enough to generalize, meaning that tomorrow, when you give me a new graph even, or new nodes that I didn't see in this train set, that I should still be capable to construct a representation for them. Right? It's as if I would be saying, look, in the case of Word2Vec, it's not very helpful if words would change all the time. In that case, you'd probably look something more like an autoencoder, where also tomorrow you can give it a new input and get a representational vector by looking at its bottleneck layers. Right? So every time when you talk about representations or embeddings, it's important to realize, are we looking for something that can generalize to new items, yes or no? And here we are. Right, because we want this to work on unseen nodes and graphs as well. But again, we could do the same trick as what we did with our autoencoder. We could just say, well, use a normal multi-layer perceptron, use a densely connected layer, and you say, look, this layer will produce me some transformed set of features, so x1 of this node I, by using as the input the features that you gave me. Right, so I have a layer, for instance. I say, okay, for this node, you have given me 3 features, x1, x2, x3, right? So, and I then make a dense layer on top of that with only 2 nodes, and all of them, our classical approach, take the inputs, and they produce me activation values. So basically I can say, well, this layer gives me x1 and x2, 1, 1, 0, 0, 0, right? And then tomorrow, if you give me a new node, and you give me the node features, I have something that can map me to the output as well. And I can stack layers on top of this as much as I want. Okay, we know already how this works, right? So that's not very new. I can do the same thing for the edge features as well. I can also put MLPs there that say, okay, transform edge features to another representation. So I have a vector here, I have a vector for each node. And if you have features for the whole graph, also there, I can stack MLP layers to convert these to a representational vector as well, right? This will not happen like randomly, of course. At the end, there will be a loss that will get computed to make sure that these representations are valuable, right? So I will still minimize some loss, obviously, but now I'm looking at the base layers. So the MLP here is typically multiple layers, so we can go to an XIK, give me for each node a representation k levels deep with k the numbers of layers used. And same thing for the edges, same thing for the graph as a whole. None of this is actually new, right? Well, there is one thing in this whole graph that I didn't look at, or in this whole kind of representational learning that I have ignored so far, and that's the graph structure itself, right? So far I've just been saying, okay, for each node, take your features, make a representation, and you're done. Yeah, but hey, what about your neighbors? What about your topology? You want to mix that in creating that representation, right? Otherwise it's like, okay, you look at everything separately, but nothing is connected. So you want to look at these connections. Okay, so that's a problem. Now we have a couple of problems. Problem one is if we do look at a downstream task that we actually want to do, that there might be a mismatch between these representations that I have created, my embedded objects, and the task. For instance, it might be that I do not have node features at all. I only have edge features. Like nodes, I know nothing about them, but the edges, I know that these are financial transactions, and I know the amount, for instance, and I know the time that the transaction happened, and so on. Yeah, but I do want to predict something for the nodes. So how do I then take these representations that I'm building for the edges, and this vector that I have constructed for each edge, and use that to predict something at the level of a node? Or vice versa, I might have only features about nodes, but I want my label is on the edge, right? Or I have features for both the nodes and the edges, but my label is for the graph as a whole. Is this a molecule that smells good, yes or no? Right? So I have to solve that mismatch there. I can create representations for all of these things, but how do I then link this correctly to the target? Here the idea is simple. It's basically the same thing as what we have always done. We pool. Right? We use some aggregation function, like a sum or a mean, to bring things together that have to be brought together. So for instance, say that we want to make a prediction at the level of the graph as a whole. Like, is this a molecule that will smell nice, yes or no? Right? In this case, it's a little bit like the global average pooling that we did in a convolutional neural network, where we said, well, we have a whole stack of maps that we have created And now I want to scale these down, these pixels in every slice that I have, I want to scale these down to a single scalar so that I get a vector of numbers as my final representation that I can then pass to my MLP layers. Well, here, same thing. Maybe you have representations that you have constructed for all of the nodes. Well, if you then need to make a prediction at the level of a graph, what would you say? Well, sum all of these representations together, or average all of these representations together. Similarly, in the case of maybe you have only edge embeddings, which is what this figure shows, right? But you need to make a prediction at the level of nodes. Well, then in this case, the pooling happens on the edge level. So then you say, okay, for each node, take the representations of the connected edges of that node, average them together, and then you pass that representation to a final classifier, for instance, to make a prediction at the level of a node. Here is the case where you only have embeddings or representations for the nodes, but you need to make predictions at the level of the edges. Well, same thing. Then what is the representation per edge? Well, you take the two representations of the connected nodes, and there you can simply concatenate them. You don't need to average or sum, because for each edge you know that you have exactly two nodes that are connected to it, right? So you can just paste the two representations together. Here that wouldn't work, because here the number of edges per node differs. So you need to average, or you need to sum. You can't just concatenate all of them together. So that's easily solved. The second problem, that's messier, obviously, and the second problem is about the fact that we do not use connectivity, right? We can now pass these features, we can bubble them up to have a representation for nodes, edges, or the whole graph, and then at the end we say pool a bit, average them together, pass that to another MLP, and you make your final prediction, right? So in the case of my simple example, where I do not have edge information and graph information, but I do have features for my nodes, what I basically say is, okay, for every node, pass it through a couple of MLP layers, done. You get a final representation for each of the nodes. And by the way, if also the nodes carry the targets and the labels, you don't even have to pool, then basically use this representation and connect this with a final layer predicting you the probability of the node being a positive. And then you use standard MSE laws or whatever to optimize those representations. Again, problem here is that the way how, or what this MLP receives or can do is independent on each node. It only sees the features per node. It has no information about the fact that this guy is connected to a lot of other nodes that have these and these and these features. That's obviously what I want to solve. I would like to use this connectivity of the graph. We just had a simple MLP over the node features. That's what I want to fix. And what a graph neural network utilizes to fix this is a concept called message passing. And the idea is okay, rather than only using your own features per node only, we're going to do something else as well, that we're going to give to this representation building MLP over there. And what we'll do is we'll say, okay, for each node, look at the neighbors that you have. And if you have directional neighbors, neighbors that are sending their edges to you, that you basically can receive information from. So hence, that can pass a message to you. Query all of those neighbors and gather information from them. And typically, what will that information be? Their features, obviously, you don't have much more than that. So query the neighbors and get the features of the neighbors as well. Problem, we need to use pooling again, because the number of neighbors can be 1, can be 2, can be 0, can be 50, right? We can look at all of the features of those neighbors, but we'll also have to pool them together somehow. So we'll also have to average these into a single representation. And then the idea is, well, combine this representation that you got from your neighbors with your own feature vector and use both to construct a representation of yourself, right? So not only do you only look at yourself to construct your representation, also look at your neighbors. So a generic formulation is this. So rather, this is the same as this MLP that we saw previously, so hence still to construct your representation k layers deep. Before, what we had is we said the only thing that we need is a stack of MLP layers only utilizing your own features, right, at k-1. And that's how we construct your representation. Now we change this. Now we say, well, we still utilize your own features, obviously, we still need those, but we also do something else. For all of your neighbors, right, we're going to aggregate information that we get from them. How do we get information? Well, we will run some function, right, on that neighbor, and we will make this, or we'll give as an input to that function your own features up until this representational layer, right? But at the first layer, meaning those are your input features. If you're at K1 here, then this is 0, right? So then these are your features. The neighbor's features, that's the information we get from them, right? And also potentially the edge features that we have as well. Aha, yeah, we also have those that can also play a role. What does that mean? So before we basically only had this, right? And this gamma here at the left-hand side, that's our MLP, basically. It's a kind of a generic description of, okay, this is something that can learn. This is something that has weights, this thing. So before, what we had is our input at the first layer, I'm only going to do it for the first layer, is this X0 thing. So the features of the node I, connect this to an MLP, first layer, right? So this MLP thing is this gamma thing that I have there, right? So that's our MLP. It only uses xi k minus 1, 0, right? And produces me a representation x1, right? Doesn't look at connectivity at all. Now what I'm saying is, yeah, but wait a second. Now we're going to have an MLP that receives indeed your own features k minus 1, but also a couple of extra pieces of information. So this aggregated thing, an additional vector as well. Where does that additional vector come from? For all of your neighbors, j, and maybe you have 3 neighbors, right? So j1, j2, j3. We will construct or we will extract some information. I said, well, the information, we could just take the features themselves directly of these neighbors. The x, j, 1, 2, and 3, we could use those directly. But we even make this learnable as well. And we say, well, the information that you bring in from these neighbors is also something that should be learnable. We want a network to figure out how it should bring in the information of each neighbor. Not just directly copy in the neighbor's features, also learn how to bring that in. So that our network could technically decide that perhaps in some cases, if you have 3 neighbors, then maybe one neighbor is unimportant. We want a way to give an importance score to each of those neighbors and to make that learnable as well. So how do we do that? We say, look, what is the information that we have? For each neighbor, you have the features of that neighbor. So give that. You also have your own features as well. So you also have your own x of yourself. So this is of the neighbor j1. This is of myself I. And you have the edge features as well. Maybe just a simple weight. Right? If you don't have that, you leave it out. But maybe there is like an edge weight, 0.8 as well. And then you say, and that is this phi k symbol there, also make this learnable. So also this has weights. So feed all of this in, also to an MLP. And this MLP will spit out the representation of the information that we want to pass. And this thing can learn and can basically say, if your age is 18 years old, and this neighbor is 80 years old, and even although the strength of the connection is pretty high, I'm basically going to ignore this at all, because it doesn't matter. Yeah, you're connected, but this connection doesn't matter. That's what this MLP needs to do. So for each pair of neighbor with you, it tries to figure out what's the message that I need to pass. So this is the representation of the message. And I do this, so I get a message for all of the 4 neighbors. So hence, 1, 2, let's say that my message is 4 activations long. So for each of the, I had 3 neighbors, right? So for each of the neighbors, I have a message. And now to this thing, at the left-hand side, this gamma thing, I say, well, you also get all those constructed messages as well. So that's a very generic formulation that uses everything, and now you're learning from your neighbors as well. We can rewrite this a little bit. You don't need all those pieces all the time, right? You can rewrite this a little bit, and you can go for something like at the bottom there, where you say, well, so that means that this might work, right? I could say, okay, for all of my neighbors, and let's include myself as a neighbor as well, right? Sometimes, depending on the way how you actually want to instantiate this generic form, you can decide to include yourself as a neighbor or not. Let's do this, right? So for all of my neighbors, what is the aggregation that I will do? I will make a sum. Right? So loop over all my neighbors and myself, right? And I also lose this thing over here, because anyway, I'm looping over myself. I'm included as a neighbor. Take the feature vector of that thing, multiply it by some weights, specific weights for every pair that I have here, stick this through an MLP, and that could be my graph neural network unit. And indeed, this reminds us of something, this sum of products that we have, where we kind of sum and we use kind of a sliding thing here. This reminds us of a convolutional neural unit. Right? It's exactly the same thing, where we also take the neighbors or the pixels in a kernel, and we take the product of each of the pixels in the window that we overlap, we sum them together, and we say this is the representation of this spot in the image. Same here, this is the representation of this node in the network. There is one issue if we would do it this way. And I would ask you, can you see what the issue is? But I think it will be pretty hard to spot. If you look back at the weights that I needed to define a convolutional unit, the kernel, right? We said there the size of that thing was like a 3 by 3, for instance. And every time I make this sum of products, in every pixel, the neighbors, well, are in a 3 by 3 zone. 9 pixels in total, and I always do the same thing. What is the issue here if you look at kind of this kernel of weights that I have here? The issue is that it's not fixed, right? And also here, even worse, it depends on the number of neighbors that you have, and here even you would have to predefine it for the whole graph. So again, if tomorrow you would get a new node that enters there, you don't know what the weights are. So we're close, but we need to set this up in a way where we don't make the weights specific for each JI pair. We use standard global weights and weights that should work on every neighbor that I get. So what I actually want to do is I would like to have some convolutional kernel, but now where I can no longer say that my neighbors are fixed, but that my domain is irregular, right? And indeed, once you then set this up, you can even convert like your standard pixel grid to a graph as well, where you say, well, every pixel has 9 neighbors, or 8 neighbors, including itself, 9, right? And that's something that I want to go for, except that in a graph, yeah, the number of neighbors is not always the same. It differs per node, right? So I need to be robust for that. So here is a drawback. So hence, I need a gather function with weight sharing. I can't just use a predefined huge matrix of weights for the whole graph, because I work in an irregular domain. Then typically we can talk about spectral approaches and spatial approaches. So I just described is a spatial method that works based on this message passing that I've just described to you. If you then want to build up richer representations, typically you can say, well, this neighborhood here, or I will go back to the generic formulation, these neighbors, these are direct neighbors, typically. So how then can you still allow, if you think about our propagation story from before, maybe there is a node that's very important in your network, but he's not directly linked to a lot of nodes, right? So with your standard message passing, he can only pass the message to this node, but maybe the influence of this guy is so strong that you actually do also want to kind of know that he will pass the information to the rest of the network as well. Here you don't have that. If you go over the neighborhood, you only look at the direct neighbors. 2 ways to fix this. Number one is with the spatial methods. Number one is, but be careful. Remember that we don't just have a single layer where we do message passing. Just like in a convolutional neural network, we didn't have a single layer of CNN units. We stack multiple layers. right? And this widens the receptive field also here. The first time, indeed, you can only message pass from this node to that node. But then if you do it again and you build a representation on top of that representation, this node can then also pass to the rest of the nodes. So the effective field of or the receptive field of a GNN network, just like in a CNN setup, is equal to the number of layers that you add in. The more layers, the more that information can spread throughout the whole graph. Some people don't like that and say, yeah, but for large graphs, well, depends a bit on how far and wide does information really spread in real life. Maybe not thousands of hops. You also know about the 6 degrees of separation kind of theorem that says that we're all connected only by 6 steps with each other. So maybe 6 layers is sufficient. That's kind of the mindset of the spatial methods. The spectral methods, then, they say, well, what we could also do instead is we use 1 layer, but how about we change this neighborhood function a bit, and we make that just more global. Instead of looking at your direct neighbors, why can't we look at the whole graph, for instance, and we give weights when we look at the other nodes? Yeah, neighbor, who is to say that your neighborhood is only your direct connections? Right? So they widen that definition of a neighborhood by first translating the adjacency domain to the spectral domain. More difficult, more computationally expensive, less intuitive, less used. But those are kind of the 2 mindsets here. So this is what I just described, like these neighborhoods. It's the same as a CNN, receptive field, and so on. I already mentioned that. So this is our generic form. Here it's a bit rewritten, right? But that's the thing that we just saw. So basically, kind of reconstruct representations now for each node in this case, but the same kind of property can be used to construct representations for the edges or for the whole graph. This formalized per node, but using this message passing concept. And then the actual units like LSTM and GRU, once you know the concept of an RNN, you have different instantiations. Well, same here, you have different instantiations of this generic idea, right? Because maybe you do not have any edge information. Well, in that case, you will not include it in there, right? So what are the ideas that have been proposed, for instance? Well, here is one of them. It's indeed you take the sum. So it's very similar to this convolutional filter that we saw previously. So you take the sum of all of your neighbors, including yourself, so you don't consider yourself, and in the generic formulation, this kind of highlights that, no, you're still special on your own, and then there is something that you gather for all of your neighbors. Well, in this instantiation, it says, well, no, you're not special, you're just one of your neighbors. And we do the same thing for everybody, both yourself and your neighbors. What do? We look at the strength of the connection, right? So you do need an edge weight. What's the strength between you and yourself? Probably something equal to 1. Right? You're most similar to yourself. So we look at the edge weight, we look at your feature vector, we have a normalization factor that we do there. We sum all of this bunch together, no weights here. So hence, why this was wrong here, we multiplied by a weight, but then was dependent on the j and the I. We kick that out there. We first make the complete sum, and then we multiply this with a set of learned weights. So here the learned weights are over here rather than in there. And now these do not depend on j and I. These are just global weights. So then we can use weight sharing there. So that's one way. How will this work if you do not have edge weights? Well, probably less well, right? So this assumes that you have edge weights and that you have node features. Interesting to kind of think about is if you try to convert this back and you look at these weights, or these then part of the update function, or these part of the message function. In other words, are these weights that are in here, or are these weights that are in there, right? And I think the answer is relatively clear because they do not depend on the neighborhood, so they're part of this function. GraphSage is pretty similar, or is another idea on this. So if you look at a library such as PyTorch Geometric, and you look at all the kind of implementations that they have, how do they differ? Well, it's in the instantiation of this generic form. So this is GraphSage. Similar idea for every neighbor, aggregate something, concatenate something, and update the representation. So basically it boils down to this. GraphSage says, okay, to update your representation, we look at your own features. They get their own weight matrix. So here they come with 2 different sets of weights. And then for your neighbors, so now we do not consider you to be your own neighbor. We do something slightly different, right? So you get your own weights. And for the neighbors, we first take all of their features. We simply take the mean of all of them. So we don't do anything special like here. We first just take all the features, we average them, and then we multiply them with their own weights. And the neighborhood function here applies sampling. Sampling is something that GraphSage introduced Because what was found is that if you have graphs that are quite large, that this message passing step can be quite computationally expensive, right? And also what was found is that, well, if you do have, let's see if I have a good picture, yeah, like here, if you do have a lot of neighbors, for instance, well, and you would aggregate their information and just average them together, that this can also wash out a little bit. So GraphSage basically said, well, for graphs that are pretty dense, maybe you don't need to even consider all of the neighbors in every training mini batch, just sample a couple of them. So it's a way to speed up the training effectively. And then in newer packages like PyTorch Geometric, they basically said, well, the fact that you define this neighborhood here in such a way that you apply sampling, this is not specific to this implementation. Actually, also with this one, you could do the same thing, right? You can apply sampling on any kind of implementation that you have. So these are actually two different ideas. So hence why in newer libraries, you can pick any type of GNN unit, and you can apply any type of sampling. And that's a way to make sure that the training can still work effectively in your GPU's memory. If you wonder, do you have attention-based mechanisms here as well? Yeah, indeed, also, and that comes then more into play to what I described here. So that would mean, okay, I give all of the information of your neighbors, and I have the information about yourself, but in the more simple approaches, what you see is that, well, first take all the information from your neighbors and average it together. And I just described to you, yeah, but maybe you also want to learn that depending on who that neighbor is, they should get less or more weight in that aggregation. And here we don't do that, they all get the same kind of importance. If you introduce an attention-based mechanism, well, then you can first say, well, first try to give attention scores to each of your neighbors, right, using again a self-attention strategy, to kind of multiply this with a softmaxed attention score, meaning that maybe for some of the neighbors that the vector will become very close to 0 and hence will not play a high importance in this aggregation. So then you also learn the importance of every neighbor towards everybody else that they message pass to. More computationally cumbersome, obviously, you introduce more weights because now you effectively also want to learn to figure out how important neighbors should be rather than something quite generic, but has also been applied. If you open the cheat sheet of PyTorch Geometric, you can see that there are a lot more layers there as well. This can go quite far, right? So layers or units will also differ, for instance, in the sense of things that they support. You have noticed, for instance, in this formulation, that there are node features in there, but that this thing completely ignores edge features. No edge weight, no edge features. In this example, it takes care of edge weights, but what if this is a complete vector of features? Then you need another unit. If many of these also assume that your networks are homogeneous, meaning every node is of the same type. We have seen last time that maybe you have heterogeneous networks where you have two types of nodes, both customer and credit card or whatever. You also have GNN units that can work with heterogeneous setups as well. You basically need to be a bit careful in your message passing that you might want to build up separate representations per node type because they come with different sets of features. So you can't just average in the same way as you would do here, for instance, because sometimes these nodes have 3 features for the first type, and then for the second node type, they have 5 features, so you can't multiply by the same weight matrix anymore. You need a separate weight matrix in this case, both here and over here, per node type, right? So you can expand these implementations so that they work on heterogeneous graphs. Does exist, right? But hence why you have these different units. They come with more weights. They are a bit more computationally heavy, but they can work out of the box relatively cleanly on heterogeneous graphs. All of the manual featureization approaches that we have seen so far, if your graphs become too complex, they would start to break down. At least here, theoretically speaking, you have the computational power, or you have the theoretical kind of description that can handle something like that. And I think that last time I also spoke about hypergraphs, where edges can involve more than 2 nodes. You even have some GNN units that can handle hypergraphs as well. And you can kind of see why, right? It's basically a change of how you define like that neighborhood and that message passing function. Now you basically just say, okay, nodes, edges can have more than 2 nodes, and we just iterate over them. So this is the general pipeline. So once you have these representations, either for your nodes, your graphs, your graph as a whole, or your edges, then on top of that, you use those embeddings, you design your loss function, and the thing basically learns to construct those representations itself. So as some examples of learning tasks, I already kind of went through this, but for instance, for node level, predict a binary label for each node. Will that node churn in the future, yes or no? Edge level, if I have two nodes, what is the likelihood, for instance, that these two guys will be friends? Presence of an edge. Or you might predict, okay, now I see that there is an edge, what's the likelihood that they will break up in 3 months from now, right? So all these kind of tasks can be quite elegantly set up because you have these embeddings or these representations that you can put any kind of right-hand side of your architecture on top of. And even graph level, pool all the nodes, average them together, pool all the edges, pool the whole graph information, and predict something about the graph as a whole. Is this a nice-smelling molecule, yes or no? Will this protein work on this disease, yes or no? So also here, I already mentioned this with inductive and transductive learning, but same thing here. Normally in the transductive setting, you will mask some nodes, you will evaluate on the masked nodes, you will make sure that you then do not use a GNN unit that would say, for instance, why don't you also look at the labels of your neighbors? So that we don't do, right? We look at the features of the neighbors, that's fine, and we evaluate on the masked nodes. But the thing in this setting that we do not really test for is, of course, the fact that, well, we assume this structure to be fixed, right? And it might be that if you use something like an attention mechanism that your learner has figured out, look for nodes that have 3 neighbors, that maybe those are more important than nodes that have 10 neighbors, but that in your test graph, the situation is completely different. So you might overfit on topology, basically. Happens rarely, it's more of a theoretical aspect, but better is to have 2 separate graphs for training and testing, as mentioned. So I already went through this, basically. Last part is a bit to talk about tooling, also with regards to the last assignment. Also here, similar as to the big data discussion that we had. Also here you find tooling that has more to do with the plumbing and the management and the infrastructure, and tooling more related to the analytical part. I think for the graph aspect, either you do something very manually to featureize from the graph, or if you want to take a deep learning based approach, the tooling in a lot of cases is PyTorch geometric in that setting. That's kind of the most best or most expanded library of GNN units that you can find at the moment. Now, in a more, let's say, overall setup, tooling then typically also involves the storage and the querying of graph-based data, and then probably also some business intelligence tools to wrangle with graphs, to visualize them. I already mentioned graph layout tools. And in a lot of cases, when people try to sell you network analytics, don't be surprised that that will boil down to be a very visual tool with a bit of search capabilities, a bit of filtering capabilities that you can play a bit with, which is fun, but also realize that, of course, true predictive tasks are possible as well on graphs. Always a little bit, and also for assignment number 4, it's mentioned in the instructions as well. With graphs, there is always kind of a risk that you will open up the visualization, you will give it a bit of color, a bit of sizes, and you end up with an enormous hairball. And you will tell in your story, wow, look how fancy and amazing and how cool that this graph looks. Yeah, sure, but what is it actually showing me? I can't really see anything here. And in every graph, you'll say, look, but there are some important nodes in the middle. Yeah, but in every graph, when you talk about the social network, there will be some important nodes in the middle. So be a bit careful in your storytelling of what you want to zoom into. Showing the whole thing on a slide is cool to look at, and I'm guilty of it myself in my last slides, but for the assignment, don't do that, right? It's easy to do, and it doesn't really tell so much. So I think, yeah, in Python, you have a couple of options here, like NetworkX and iGraph are more classical approaches, let's say, or traditional approaches for wrangling with graphs to extract features from them and so on. For deep learning, I think, well, it's PyTorch geometric. You have a couple of others, but by far that's the most important one. Spark has graph support as well, not so commonly utilized anymore. For visualization, you have a couple of choices. Things like Cytoscape, Graphis, Gephi, which you're kind of recommended to use for the assignment. You don't have to. If you would like to make your own vibe-coded web page and you use that to visualize, fine by me. Gephi is not always the most easy to use tool, but it's one of the few that can kind of handle larger graphs. And then to store graph-based data, graph databases like Neo4j, memgraph, and many others are quite popular as well. So this is GraphX. It's a newer component, let's say, in Spark, and it's kind of the same idea of we want to bring machine learning to graph-based formats. Same as with Spark Streaming and with MLlib. They first did that on top of the very low-level RDD API, and then they never kind of went around to implementing it on top of their data frame API. There is a package that does that, but it's external. Didn't really take off. There are companies working with GraphX, so they do. I mean, they do exist, and that they use Spark for graph analytics as well. But it's not the most kind of let's say pleasant way of working with graph data. The graph databases, then, we already had our whole discussion on Hadoop and MapReduce and so on. And so to link a little bit back to this, what was happening around the same time is that there was a phenomenon rising up called NoSQL, where they met in the middle, thanks to MapReduce, but where this was more from the big data angle in Hadoop, and NoSQL was more a reaction to the traditional relational databases, where people said, well, they have some issues. They are, the traditional database world is good at querying, it's very safe, it's very robust, but they're not so good at scaling out. And what we would like to have is this horizontal scalability, same as what people were trying to do in the Hadoop world, where we can just add servers and we can easily scale out. Maybe with less guarantees in terms of consistency, but that's okay. We're willing to live with that. What the NoSQL world also, the suggestion might be is that they don't like SQL, but sometimes they did keep that. But what they also considered is, well, we don't like the fact that you first need to design a complete description of your data that you will store, a complete schema. It should be possible to just start dumping data and then playing with it immediately without some imposed schema on that. And indeed, maybe SQL is something that we don't need, but we will just write our queries if necessary using MapReduce. So this was kind of a counter-reactionary movement, let's say, to the standard relational databases. Now, these relational databases, they are pretty old, but they keep the world going. They're still very alive today. So the whole kind of idea that they would be replaced by NoSQL systems didn't really happen. They still have the majority of market share. But indeed, it's true, they heavily impose the creation of a schema. They're heavily oriented towards tabular-oriented formats and so on. So they do come with a little bit of baggage, which is not always that nice. And the way how this links into the graph database story is the majority of the NoSQL vendors at the time, they were mainly following kind of the Hadoop idea of working. And they were saying, well, we are going to create key value stores, as we saw last time, like HBase and so on, and that can be heavily distributed. And then, yeah, if you do want to run a complicated query, pity for you, use MapReduce. And so hence why people didn't really like it at the end. But that was the majority of kind of this NoSQL idea. But there were a couple of others that said, you know, instead of moving away from the traditional relational database and simplifying it, how about we even make it more complex? And we go towards a data model that instead of moving from a relational data model where everything is stored in tables and simplifying that and we say, okay, everything is a key value pair, how about we take this and we try to increase the complexity a bit so that it allows us to store richer forms of information. And the classical example of where sometimes a relational database does not really match with your vision of reality is the fact, okay, let's say you have a table where you want to store what is it here? Books, right? And you want to store information about books. So you have the ISBN number, the date of publication, and the title of the book. And then you have a table where you keep track of authors, for instance, and you have the names of the authors. And then you can link those tables together, and to know which book was written by which author, you see here an author ID column that appears, and that's like a reference to the primary key in this table so that you can look up the information of the author for each of those books. And then the classical situation happens where people say, yeah, but wait a second, what now? It's possible that a book can be written by multiple authors, right? And you can just stick multiple identifiers in this table there that would break one of the assumptions of the relational model. So instead, what you need in this standard paradigm is to create some sort of an in-between table. And where you say, fine, I have my books table, and there I have the identifier of my book, 1, 2, the title of my book, and so on. I have a table where I keep information of my authors, and also those have an identifier, 1, 2, 3, and so on, have a name, year of birth, and so on. And then you have this kind of weird table in the middle where you both put book ID as a reference to books, and you put author ID as a reference to authors, and then you can say, well, book 1 was written by author 1, and book 1 was also written by author 2. And you keep track of those connections, these many-to-many connections, in such an in-between table. Yeah, that's nasty. Huh? That means that whenever you want to do a query where you need both information from books and authors, that you need to go through this in-between table that you have there. We know if we would have a full graph-based data model in mind, actually that would be an easier way to do this. And in a graph-based setup, we might say, look, you have two node types. You have an author node type, and this is kind of my meta schema, and you have a book node type, and the edges are keep track of which author has written which book. And then in your instantiated version of this, so your actual data contents, okay, you might have two authors, author 1 and author 2, and you might have two books, book 1 and book 2, and you have edges that do something like this. And then naturally you can keep track of all of these appearing connections without this kind of weird relational structure. We call this relational, but actually this is more relational. If you want to keep track of relations between things, nothing can be better than a graph kind of data model. And that's the idea that these graph databases within the NoSQL kind of mindset came up with. And then they also said, and you know this SQL thing, also this, instead of doing away with this and kind of forcing you to write MapReduce, we like this. So we're going to keep this, and we're going to come up with a query language that is specifically designed to be used for these graph databases that we're building. So yeah, this I already kind of described a bit, so I will skip a bit over this. You can read this. So the most interesting category, if you want to kind of differentiate between the relational kind of traditional databases and the new ones, yeah, distribution, easy to scale, a lot of focus on scalability, a lot of focus on maybe being less consistent to reach that scalability, very often simple APIs, very simple querying facilities, and so on. But then very simple data models, key value, document-based. For us, okay, yeah, if you really need that scalability, that's important. But the most interesting part are the ones that kind of went the other way and said, we're actually going to make the data model more complex than what the relational databases are offering us. And today, well, all these early adopters of NoSQL, things like MongoDB and Redis and so on, it used to be that this was kind of the new hype, and everybody needs this because everyone wants to be scalable. I think also today there is a little bit of more nuance, let's say, where people have figured out that these relational databases, that they were not so bad to begin with, and that consistency is very often a good thing to have. So also there, these early adopters were confronted with a bit of sore lessons as well. And today, people don't really talk about NoSQL anymore. There is this new term called New SQL, where it's kind of, okay, let's take the best ideas that these NoSQL databases brought to the table. Maybe the fact that you don't need to create a schema from the beginning so rigorously. Maybe the fact that you want to store JSON in a database column. Maybe the fact that you want to have some possibilities to scale out or to maybe give less importance to consistency aspects. So today we see that there has been like a merger of those ideas, and that a lot of the traditional relational database vendors have taken ideas from this NoSQL movement. So things have a bit settled down. But still, for us, the most interesting ones are the ones that made the data paradigm a bit more complex. And for instance, those are databases where they said, you know, we're going to focus specifically on time series, for instance, complete with, for instance, our own querying language, sometimes an extension of SQL, sometimes their own query language, to make sure that you can do very powerful data wrangling with time series information. Vendors of, for instance, systems that are being used at stock markets At trading floors, for instance, things such as KDB+, they heavily invested into this kind of thing. And indeed, this is a smart idea in the sense that more traditional relational databases, that they have some issues to really be efficient and easy to use and performant enough, especially in cases where you need to monitor a lot of time series and where a lot of events come in per second. So that is one niche where actually the idea to go beyond the things that a relational database offers and to make it a bit more focused actually was a good idea. Similar for geospatial databases, where you say, okay, if you think about things that you need to represent by polygons, lines, 3D structures even, and the types of queries that you will do with these objects, like calculating distances between them and making buffers around them and checking whether one polygon is contained in another polygon. Also there, that's something that a traditional relational database is not really good at supporting. SQL has no built-in support for these kind of queries. So let us extend what is offered by these relational databases to work better on geospatial data structures. And also this now has been widely adopted by the big players in the relational database world as well, but was also an originally good idea. And similarly, for graph databases, what I just discussed, well, instead of trying to represent a graph as a bunch of tables that you need to link together, no, represent a graph directly as a graph. And then the schematic description of a graph is basically a graph itself, right, where you list the node types that you have. You have readers, books, and genres, and the types of edges that can appear between these node types. Right? So this is not the actual content of the database, this is the description of the content of the database. Right? This is the schema. And then the actual content, you can have multiple books, multiple readers, multiple genres, and you know the types of connections that these things can have. And this does away with these nasty in-between tables that you would have in a traditional relational database. And then maybe you can also start thinking about a query language specifically for this, where questions such as, give me the friends of my friends, are easy to answer. Also something that with traditional SQL, these kind of recursive questions, not so easy to set up. And maybe here can be expressed more fluently. So that's the job of a graph database. Yeah, again, this would be how you would have to do it with the traditional books and authors example, as I just discussed. In a graph database, it would be something like this. Here I've added in the edges both ways, but you basically only need one of those. So that would be the alternative. And then maybe a query would be, well, what do I want to select now from a complete graph? I probably want to select a subgraph from my graph. So this query language, in this case, this is Cypher, the query language that was made originally by Neo4j, one of the most popular graph databases and also adopted by memgraph. Says, well, I want to match, give me the subgraph, where you extract book nodes, author nodes that have an edge written by in between them going that way, but only the subgraph for those author nodes where the name equals my name. And then I maybe don't want to see the full subgraph, actually the titles of those book nodes is enough. So it looks a bit like a standard SQL query, but here you're trying to select subgraphs. There are other graph databases as well, Allegro Graph, GraphDB, Infinite Graph, OrientDB. I think Neo4j and memgraph are the most popular ones still today. There are others as well. You might work with another graph database later in life, but they basically follow the same data paradigm. It might also be possible that you will not work with Cypher in the future as your query language, but you will encounter something called GraphQL. So instead of SQL, GraphQL, also a graph query language. Very often this is something that gets utilized to expose graph-based data through an API. If you look at things such as websites like Twitch, for instance, and you look a bit in the developer tools of your browser and the internal APIs that they're hitting, you will see that they're using GraphQL to get like a list of accounts that you're following and so on, and to do that sort of querying. Also interesting, a bit more cumbersome for analytical and business intelligence purposes. Cypher is maybe a bit more pleasant to use, so that's the reason why we utilize it for the assignment as well. So yeah, the graph databases, you can think of it as a hyper-relational database in a sense, because these joint tables are replaced, we don't need them, those anymore, by directly representing the semantic relations in a graph format as well. Funnily enough, Neo4j is also quite popular because it's pretty exhaustive in the sense of what you can store. You can have different node types, you can have different edge types, you can have features in your nodes, you can have features on your edges. It does not allow for a hypergraph to be created, so that's a bit of a drawback if you really want that. It does also not allow to have the same edge type appear between the same source and target node. So if you do want to represent that something happened twice, you either need to capture it in the edge features or you need to create a separate node type for this. And also in assignment number 4, there is like a node type that basically semantically represents a relationship, but that needs to be there because it can't all be captured in the edges themselves. You have way simpler ones as well. You have graph databases that just keep a list of edges, basically, which might be more faster to query, but are simpler to set up and cannot store so much information. So hence why Neo4j and memgraph are pretty popular, because they give you kind of a good base to store all of this information. So yeah, if you work with Cypher, obviously you can ask ChatGPT to help you along a bit. That's perfectly fine. But like the basic idea is that you, instead of a select like in SQL, you run a match query to select subgraphs. And then you represent nodes in your query with like parentheses, because that looks a little bit like a circle. And then you can basically select a certain node type by using a colon, like colon book in this case. I'm only interested in book nodes. And then later, if you want to do something with those nodes, you can give them like a variable, like b. And then you say edges are drawn using these kind of dashes, where you can have directionality or not. So either unidirectional or a directional relationship. So in this case, I want to get a subgraph where you give me all the book nodes, all the outer nodes, but only those where there is a relationship like this between them. So if there is an outer node that hasn't written anything, it will not be selected by this match query, because there is no written by edge that links to that. So I return those nodes to show. You can add in, like in SQL, order by statements, limit statements as well. Where style clauses, also very similar to SQL. I only am interested in a specific book node where the title matches a specific title, or you can mix them in with the statement of the match clause as well, which is kind of like a shorthand that you can use. Join statements you don't have, because you don't need them. You're not linking tables together using a join statement. So you use a direct matching in the match statement as well. So here I want to have customer names that purchased a book written by me, older than 30 years old and paid in cash. So I want a subgraph where I have customers, they purchased the book was written by an author, but the author needs to be me, the age of the customer needs to be higher than 30, and the type of the payment, so an edge attribute in this case, so a feature of an edge, needs to be cash. And then I am only interested in the names of those customers and a unique list of them. And then what makes this language especially powerful is the fact that you can follow edges more than one step, and that you can say, well, for instance, I'm interested in books that belong to a certain genre, but maybe my genres form some sort of hierarchy where I can have subgenres, right? And so I would like to say that the top genre that I'm interested in is programming, but also books that maybe were not linked to the genre programming, but that were linked to the genre Java programming, which itself is linked to the genre programming. I also want to get those, right? In SQL, that will be already a little bit cumbersome to do. Here I can simply say, well, book needs to be in genre, and then there can be any number of edges between that genre and the target genre that I'm looking for. So between 0 and as many that you want, edges to reach this node, and that node needs to be the programming one. And so things like give me not just the friends, but also the friends of friends with minimum and maximum limits are pretty easy, or easier to express with Cypher than with a traditional relational database. Now, in the beginning, Neo4j proposed itself or came to the scene and said, okay, we want to be used as an operational database. So for your day-to-day querying needs and data storage, not directly to support data science workloads or predictive workloads. But of course, over the years, they started to see that analytics was growing and data science was growing and deep learning was growing. So they kind of changed their mind, and they even made their own data science library to, for instance, offer support to calculate these betweenness and closeness and page rank metrics, for instance, because they were seeing that people were utilizing this to featureize their graphs and to use this into predictive pipelines. So now basically it's pretty easy directly on the database itself to calculate these kind of metrics. And both Neo4j have a data science library that they have implemented, but also memgraph, what you guys are using, they also already have a bunch of algorithms, so they call it MAGE, that you can run as well. So also pretty interesting to play around with and to kind of see what's in there in terms of different featureization approaches that we have discussed. You will also see those implemented there as well. Now, if you want to go a step further, obviously the idea is again then that you bring this to Python very often, or R, but typically Python, right? Where you have some packages that can be utilized to connect to an underlying Neo4j database. And once you have a connection going, typically you will use a package like NetworkX to do some further or deeper analysis on these graphs. And then also very often what you will do if you then want to go a step further in a more deep learning style of approach is that you will first make an export of the graph database and then set that up in a training loop with a PyTorch geometric. That's also a common use case. For visualization and exploration, yeah, Gephi is an old tool, but still quite useful. It's not the most pleasant one to utilize. You have some Python-driven tools as well. You have some JavaScript-driven tools. So again, for the assignment, actually pick whatever you like to make visualizations. Make sure that they look a bit understandable and clean and so on. You don't have to use Gephi. Feel free to use anything that you can find. But Gephi is still pretty popular because it includes also a lot of graph measurements and metrics that you can run on larger graphs as well. Yeah, so this is Gephi, the thing that you probably will utilize as well. And then for use cases, well, you guys are working on the Epstein files graph, but other use cases, I already mentioned churn a lot, I already mentioned fraud a lot. But obviously there are use cases that have to do with investigative journalism. Obviously Panama Papers, Paradise Papers, I already mentioned. Fraud is a common one, but also optimization things or recommender systems based on purchasing patterns. That's also quite common. So graphs see kind of a lot of use in a lot of different settings. Here are some other kind of examples of things. Yeah, something where it's also very commonly utilized is to perform analyses of spread of misinformation on social networks, of bots, for instance, that are posting fake accounts on networks such as X or Facebook and so on. That's also where you can find a lot of data sets that you can explore as well. I think, or to give some examples and then to close off with, like if over the years, what students kind of worked on in the past, and every year groups have been capable to come up with some quite interesting findings, to be honest. One of the first kind of data sets that was worked on at the time, because it was just released, were the Panama Papers, some interesting findings that popped up over there. What also we looked at in the past is like politicians need to report their mandates that they have in Belgium, meaning in which companies they're board members of and kind of roles that they take on. And based on these mandates, trying to kind of link politicians and their political parties and companies and do some kind of clustering based on that. You might imagine that the clustering would result in communities that are mainly driven by left-wing versus right-wing parties, but Belgium being Belgium, it's driven by the language of the parties. Also, Twitter bots is something that we looked at in the past, kind of to a way to spot fake accounts of Russian and other bots and which kind of misinformation that they were spreading. So that was also pretty fun. Reddit posts on COVID-related subreddits is another thing that we did. So this was right after COVID started to happen, and kind of to see in the first 30 days of these subreddits what people were posting about and talking about and how this spread throughout the whole kind of network overall. YouTube recommendations. This was linked to a piece of research that said, well, YouTube has a way to kind of funnel everybody in the same style of recommendations. So this is a data set that was constructed by running thousands of browser sessions with the cookies completely cleared and kind of just randomly clicking on videos and then seeing what the recommended videos are that you get and whether you can spot some patterns that show up over time. TikTok videos. TikTok really doesn't like to be scraped, but okay. With hashtags and videos and popularity and kind of seeing what works there, and also kind of communities that get formed there. So that was also pretty fun. Twitch streamers is something that we did as well to kind of spot popular popular games that show up and popular tags and subgroups and special niches of streamers. So that was also fun. Politicians on X, so going back to politics, it was election in Belgium at the time. So getting all the tweets of politicians and kind of figuring out what they were tweeting about and who is following whom and who retweeting whom and so on. I think last year this was games on Steam, using the whole Steam dump games and then which people review which games, play which games. So this is both games and users. Also utilized to find kind of subgroups in Steam or to maybe improve the recommendations that you get if you're a gamer and you're interested in indie games, for instance, find some hidden gems and things like that. And then now, this year, of course, it's the Epstein network. I'm looking forward and curious to see if you guys can find some interesting patterns and show some interesting results. Okay, other than that, I think maybe 5 minutes. I know that there are some questions also about the exam, right, and the way how it will be set up. So kind of to summarize the basic idea, the exam is about 20 multiple choice questions, basically, with guess correction applied. Not difficult, basically more polling your understanding and kind of being able to make trade-offs and knowing what the benefits or advantages or disadvantages are of techniques and so on. And then 1 or 2 open questions. And very often these open questions are a bit more of the creative side. Very often like, okay, imagine that you have this sort of data set, how would you approach this? Or why would this approach not work? Or why would this approach work in your view, right? And give some critical feedback, let's say, or critical insight to make sure that you have picked up the right things from the course. All the coding aspects or the hands-on aspects are part of the assignments, right? So I will not ask coding questions on the exam itself, right? So no Python code that you need to explain or write down. It's also completely useless to do that. I mean, you have a computer, you have ChatGPT, you want code on paper, so you don't need to expect coding questions there. Other than that, the difficulty level of the exam is quite all right. It's the assignments that are the hardest part, I would say, generally. So, and you're almost at the end of that. Deadline for the assignment is 31st, right? So don't forget that. There will be a page open on Toledo and an announcement as a reminder. So do remind to submit. And other than that, if you have questions, feel free to shoot. But other than that, that was it for me. Good luck with the exams. And I hope that you only have to do them once, at least for my part. Thanks a lot. Yeah, question. Yes. That's good news. I think generally speaking, if your results are more or less in line with the public part and the hidden part, that's good news, right? That means that you didn't overfit heavily, right? Also, it means you probably didn't underfit heavily. That's what you kind of expect to see, that you kind of stay in the same more or less results that you get there. So it's mainly the sudden jumps that would be a bit strange, right? Yeah. Yeah. And for the fourth one, we can pick whichever angle we want. Yeah, do whatever you want. So pick a technique, pick an angle, pick a story, and try to find something clever. But for the fourth assignment, so don't pick like the angle of, here is the whole graph, ta-da, I know what the whole graph looks like, right? So make it a bit more nuanced. Combine an LLM if you want, you have the text in there, do whatever in the time that you have left. Don't go all the way overboard, you have a limited time, but try to find something clever, interesting, and show that off. That's the idea. Other questions? Yeah? An example question of the previous years is a classic is, what makes a random forest random, for instance? That's kind of the style of questions that you can expect. And then why doesn't it give random predictions? Or what makes an isolation forest different than a random forest? Or make a drawing and explain how word2vec works. That's also an example question. Yeah, for the open ones. Yeah, for the closed ones, it's like things such as, okay, which of the following evaluation metrics is not dependent on the cutoff that you set on the probabilities? Is it F1, is it accuracy, precision, or AUC? Right, something like that. So yeah, well, of course I need to ask something. So it's not like which algorithm do you like the most. So of course I need to ask something, but that's kind of the content that you can expect. Yeah. Or what is the thing of the technique that during training randomly takes out activations of a neural network and sets them to 0? Is it dropout? Is it mini-batch? Is it whatever, something like that? Or for the open question, explain in your own words, how does dropout work? So things like that, yeah. Also another question I thought at the back, or? Yeah. No, people always ask me that, and there isn't. But that also doesn't mean that you need to, I mean, have a feeling like, oh, we need to make sure that we write enough, right? It's okay to be concise and to the point. Or if you put more figures in, of course, you have more pages, for instance. But I like figures, so feel free to put those in. I will probably put in the announcements, like if you do want to include code, you're free to do so, either in the zip file or you put it on GitHub. Just make sure that I can find it somehow. I don't really care where you put it, but I need to be able to open it in some way. Yeah? No. No, preferably not. No. No.
So you said if you want to include code because it's not mandatory to include.
For one of the assignments it is, right? For assignment number 3, because it's basically heavy code based. For the others, you can basically just give a description, but very often students like to include the code that they have used. And it's okay if it's vibe coded, I can tell, but so what every code is nowadays. And be honest about the fact that you vibe coded it. In general also, with regards to AI, for sure, ChatGPT will have given you tips for the assignments, that's okay. But do show to me that you understand what it has given you as a tip, right? If it's like, we were told to do this, but we have no idea why it works, then the learning effect is a little bit lacking there. So then go back and ask it why it did this, or why it should, or what it means, so that you also learned a little bit. What I will also do, maybe good to know, after I corrected all of the assignments, what I typically do is I post a meta review on Toledo, where for all of the assignments, I make like a synthesis of approaches that students took, things that, like, because often students are interested, especially for like the first assignment, like, okay, what did these guys do? Why didn't we do well? So I will give a synthesis of these are the algorithms that were most popular, these were the featureization approaches that students took. This worked well, this worked less well for all of the assignments. That's typically also something that is fun to read through so that you have a bit of feedback on that as well. And you know what others did as well. Also for the 4th assignment, like we analyzed this, but what are the cool things that others found? Yeah, exactly. So you can also expect this as well. Okay, good. Then I think it's time for us to say goodbye. I wish you farewell, and like I said, good luck with the exam.